Kannst du schnell mit hoch, ob du mich hörst? So, good morning and welcome to the Brain Computer Interface and Neurotechnology Summer School Day 3. Let me know in the chat where you are from and let me also know if you are hearing me. So we have people from India, from Mexico, from Leona, from France, Finland, Israel, Germany, Spain, Turkey, Algeria, Croatia, Spain again, South Africa, Pakistan. Very nice. I want to go mountaineering there. Make sure to invite me. Colombia, England, Peru, Italy, Argentina, Australia. So very nice. Welcome again. Today we have again a lot of interesting talks. So here on the screen you can see the schedule for today. We will start with Jörn Horschig from Artenis Medical System in Holland. He will show us how to use FNIRS functional near-infrared spectroscopy and EEG for the mobile future. They have a very nice wireless system. And then we have Gary Hirsch from g-tec, and he will show us how to use g-HISUS or Simulink high-speed environment to run EEG FNIRS brain-computer interface experiments with motor imagery on the sensory motor cortex and with the strobe test by looking at data from the prefrontal cortex. And then we have Oren Shriki from the Negev in Israel. It's a very famous BCI researcher, and he will show us how he extracts biomarkers for different brain disorders from EEG and with BCI technology. Then we have Adriane Randolph from the US. She's working for many, many years on brain-computer interfaces with her big lab, and she shows us how to improve human-computer interaction with BCI technology. Then we have Rupert Ortner, our team leader from Barcelona at g-tec, and he will show us how to run and analyze P300 experiments. So he will do a visual P300 spell experiment and also a vibrotactile experiment, and will show you all the processing steps. So that's also a pretty interesting example as a preparation for the BCI hackathon tomorrow and on Friday, because we have P300 data sets inside the hackathon. And then Daniel Strauss from Saarland University in Germany will show us the decoding of spatial auditory attention. He's working for many years on this topic, and I'm looking forward to his presentation. And at the end, I will show you how to configure a brain-computer interface. So I stop my presentation here and will look for Jörn. So I can already see him in the panel list. So I unmute him and ask him to share the video. Good morning, Jörn. Nice to see you.
Nice to see you too.
So I can see you and I can hear you. Please press on the share screen button in Zoom. So your presentation is loading. I can already see it, and please go ahead.
Okay, thank you. Good morning, everybody. First of all, I would like to thank g-tec for this wonderful opportunity in Great Summer School with very interesting talks. I would like to talk about combined NIRS EEG for a mobile future. Every one of us is working for a better future in a certain sense. However the future will look like, we all strive to make it better than today. And most of us might not have a clear vision of the future, but every one of us might have a clear vision of a certain aspect of the future. So some of us might think of futuristic cities, and others of us might think of cybernetic implants, synergies between technology and human. The reason why we think about this aspect mostly is because we all work on neurotechnology, research and development. But of course, we're not the only ones thinking about the future. Also, the mass media and researchers, they think about the future alike. So this is a screenshot of Back to the Future 2. And here you see Doc Brown. he used a neurotech tool he called the sleep-inducing alpha rhythm generator, which according to its name induced alpha waves to induce sleep. And he used this tool to counteract the sudden panic of Jennifer, which you see on the left, who got a panic attack because she suddenly realized she's in the future. So the device Doc Brown was using was developed in 2015, according to Back to the Future. So we're a bit late. We don't have this yet. But, well, let's see, maybe we will get there someday. So how does research actually help to get there? So usually research starts with some kind of evidence or some kind of idea we have today. Often we have a certain status quo, and then we identify an issue or problem which we want to improve. The problem can be a lack of knowledge, a mismatch between observation and theoretical functioning, or, for example, a lack of rehabilitation techniques, which we need to improve. So since I moved from the research, from academic research to the industry and also taking business classes, I know that we shouldn't talk about problems, but we should always talk about opportunities. So let's rephrase a bit. Given the current status quo, we identify an opportunity to improve the status quo. We're not always altruistic, so some of us only want to do this for a thirst of knowledge, but that's perfectly fine. In essence, we don't need to have a direct aim to improve the future, but it just happens. Well, the tool that we use is research and development. So most of us are working in research and development, and this is actually our job for most of us. At least I assume that it's the most of the people that are now listening to me. Because this is what we know and what we're capable of. And using the tools from the research and development toolbox, we investigate the original question at hand and then strive for the most optimal solution. And that inevitably builds a small part of the future. It may not seem very important, and it can be a very small part of the future, but it is part of it. And as it usually is with the future, as soon as we are in the future, it's already in the present, and then it's already in the past. So the cycle is then complete and repeats itself again. So while this is all perfectly logical and makes sense if I explain it like this, we have to ask ourselves if what we're doing really matches this cycle. So the methods and techniques and insights, will they really be used in the future? And for that, I would like to give you an example of how researchers usually see their field and the application of their research. And I will use an example that I used myself during my research as a PhD student. So I study visual attention, and I used the following example to explain the research to my family, but also to make clear to funding bodies why my research is important for actual life. So I always started like this. I said, imagine you're driving on a street and you need to pay attention to the street and the traffic in front of you. And there's a green traffic light. And you need to pay attention to the green traffic light because it might turn red. But at the same time, you're not driving alone. Your beautiful wife is also in the car and might talk to you and might need your attention. But you still need to attend to the traffic light in order to avoid possible traffic accidents. So you need to inhibit, or you need to somehow make sure that your visual system inhibits your wife to a certain extent, not too much, obviously. And you attend to both your wife and to the traffic light. So this sounds like a valid example, I hope. Of course, for funding agencies, I also explained then that the insight of my research can be used for elderly people or for children with ADHD disorders to study why they have attention deficits in certain situations. Of course, it sounds really useful, but it's of course very different so what I did was very different from this example. I didn't study driving a car. This is an example of a paradigm that I actually used. And I studied the difference between attention and distraction. So participants had to attend to one side of the visual screen and discriminate the color of the square on that screen. And the longer they paid attention to that side, so the longer they paid attention to that side, the higher the likelihood was that the gray square on the unattended side turned color to either blue or red. And if they detected that, they had to switch attention to that side and from then on report color of the square on that side. So this is let's say a more or less elegant paradigm to study visual attention and visual attention switching. However, it's obviously vastly different from the situation I just explained. This is much more controlled. There's only rectangle squares on the screen. And the closest resemblance to what I just explained and what I'm showing you now is maybe the red color, which could be on the traffic light and is also in my experiment. So it's not really close to what I used for explaining what my research is actually about. Another huge difference, obviously, is the environment that was used in the study. In most studies, a controlled lab environment is used. So as experimenters, we usually have every aspect of the experiment and of the subject under control, like where and how the subject is sitting, where the subject is looking. I even instructed my subjects when to blink with their eyes and when not. From a scientific point of view, this makes perfect sense because we want to be a control freak. We want to have as little confounding factors in our experiment as possible. And for answering a fundamental question, that's the only way to go, and that's perfectly valid. However, it doesn't really fit to this scheme. So my studies were far away from real-life naturalistic scenarios. It was not like the scenario I was describing my research with. I'm not saying that that's bad. I think it's quite essential for certain kind of studies, for fundamental studies. But I think if we keep on conducting research in that manner all the time, then we need to have an additional step in this cycle. So we need to have a transition to reality. We need to know how to apply the knowledge that we actually got from this fundamental research and how to apply that into real life. Sometimes we cannot easily translate a paradigm from a lab to real life. So, for example, driving a wheelchair using a brain-computer interface is not done in a controlled room in real life. It's much more complex. There are much more distractions, much more things happening. So I want to give some examples on what I actually mean with naturalistic environments. So as a company, we focus on building wearable neurotechnology. We specifically focus on near-infrared spectroscopy. And I will explain what the technique means in a bit. But our specific focus is on making devices small and portable. And of course, high quality, always. We're not the only company doing that, but I only have limited knowledge and a limited view on what other companies are doing. And I know pretty exactly what we are doing and especially why we are doing that, which is why I'm now obviously focused on our techniques. Artinus is heavily research and development oriented. So we have more than half of our employees working in research and development. And following this approach, we allow researchers to conduct both fundamental lab-based research, but also studies in naturalistic environments. So on this picture, you see a colleague of mine with his son, Lucas. And both are wearing the Bright device, which is fully head-mounted, as you can see, and allows for free movement. And the device is very comfortable. So it allows Lucas to play as usual. Now I want to show you a video of that. And then know that videos using online tools are not always the best idea. But I still hope that you can see a little bit of how comfortable it is and how Lucas likes it. Obviously, it doesn't work now. Okay. Then I'm going to skip it. But he really liked it, as you can see on this picture. So in the video, you would have seen that he wears the device, just plays regularly with his toys. He really doesn't care. So it opens up really new avenues of research in a certain sense. So using the device, we can record data directly during father-son interactions also, or just let the son play, let Lucas play, and record his brain activity. And if you now start to control the playing environment, the usual playing environment, just a little bit, maybe place specific toys there, maybe add an eye tracker and motion capturing, then you get a very deep insight into how children actually play. And you can add certain tasks to it, and then you have a very specific, controlled but naturalistic environment. We're actually doing this, so exactly with children, with infants, in an EU-funded research project with academic and industrial partners. And it's really quite interesting, quite fascinating, because it just opens up a lot of avenues. One other reason why we focus on mobile devices is because half of our customers are sports scientists. And sports scientists do have to study the subject of motion. So for us, it's quite natural to have mobile naturalistic studies, because that's what half of our customers were doing anyway. And now by developing the mobile neurotechnology, we can take that also to the neurotech domain. Some of our customers even go one step further and use our wearable NIRS devices to go into the wild directly. So on the left, you see one of our customers who climbed a mountain with the device and measured his brain oxygenation during that, to measure hypoxia. On the right, you see a free diver, professional free diver, and we measured the brain oxygenation during free diving. So there's all possible just because we have wearable neurotechnology nowadays. I want to now talk a little bit about the company and about the technique itself, because some of you might have heard about NIRS, but are not exactly sure what it is. Some of you might have heard about the company that I'm working for, and some might have not. So the company is called Artinus Medical Systems. It's the only company in Europe that develops and distributes NIRS devices since 2002. We're located in Elst in the Netherlands, which is very close to the German border. If someone asks me where it is, I will always say it's between Cologne in Germany and Amsterdam in the Netherlands. We have about 40 employees. And as I said, about a bit more than half of them are working in research and development. So we're quite focused really on research and development. Our key markets are sports science and neuroscience. The technique that we're using is called near-infrared spectroscopy. Near-infrared spectroscopy measures something like a bolt-like response. And to be more precise, we measure changes in light absorption in a volume of tissue. And from these changes in light absorption, we can calculate changes in concentration of oxygenated and deoxygenated hemoglobin. And that in turn tells us something about brain activity. And the principle that we use, changes in light absorption, is actually known for centuries already. This is a picture, Joseph the Carpenter by Georges de la Tour from around 1642. You can see it in real life in the Louvre in France, Paris. And already here, it was obvious to the painter that if you hold your hand in front of a candle, so in front of a light source, your hand shines red. And that is not because your blood is red, but it is mostly because your tissue absorbs nearly all light apart from the red light. So our human tissue is relatively transparent for light in the red and infrared region. And that's the core principle that we use. So we want to know two unknowns. We want to know the concentration of oxyhemoglobin and deoxyhemoglobin. Traditionally, in this graph on the right, oxyhemoglobin is the traces of oxyhemoglobin are in red and the traces of deoxyhemoglobin are in blue. And in this graph, you see the absorption coefficient. So it's the absorption spectrum of oxy and deoxyhemoglobin. And in addition, I added water, the absorption coefficients of water. And the human visible light ends at around 820, 830 nanometers with the red light spectrum. And there's a certain optical window in the near infrared spectrum that is between 700 and 900 nanometers. The reason for that is that the human tissue, the biological tissue below 700 nanometers is the main absorber. It absorbs a lot of the light, which is also the reason why if you see the hand in front of the candle, it is red and not blue or green, because the blue and green light were absorbed by the rest of the biological tissue. However, wavelength above 900 nanometers are then mainly absorbed by water, as you can see in this graph, in the yellow trace. Which means there's a very narrow window only where light actually passes through the human tissue. And that coincidentally is the red light and near-infrared light. And it's called near-infrared because, as I said, our vision ends at around 820, 830 nanometers. And then the infrared light spectrum begins, but it's just the infrared light spectrum. And as I said, we have two unknowns, so we need two observations. What we use in our devices is two wavelengths for that. And we use one wavelength at around 760 nanometers. That is where the local absorption maximum of deoxyhemoglobin, here in blue, is. And we use one wavelength just above the isobestic point. That is the point where the two absorption spectra cross, which is around 850 nanometers. And if we now have these two unknowns, then we can, two observations, we can now calculate the two unknowns. And that is under the condition that everything else in the human body stays roughly constant. So we know, for example, for brain activation that nearly everything stays constant, just oxy and deoxyhemoglobin changes. And that is why this technique is valid. Further, NIRS makes use of two physical phenomena. One is called scattering, the other attenuation or absorption. So if we shine light into the tissue, we know that certain photons get absorbed and the light that comes out of the tissue is a bit weaker. But also you probably know that if you shine light into a tissue, or usually if you shine light, it goes in a straight line. Whereas if you shine light in a tissue, for example, in a water bottle, then it starts to scatter in all different directions. So this means that light doesn't go in a straight path anymore, but it bounces back and forth. And the NIRS technique makes use of this because the human tissue is also highly scattering. So we shine light into the tissue with a transmitter, then it bounces a bit back and forth, and eventually it reaches a receiver, which you can see here. We usually place the transmitter and receiver about 30 millimeters apart. The reason for that is that we know that the measurement depth is about half of the interoptical distance. So if we have receiver and transmitter 30 millimeters apart, we know that the measurement depth is about 50 millimeters. And if you know a little bit about neuroanatomy, you know that the neocortex is about 10 to 15 millimeters away from the skin, which means the distance that we use is just enough so that the light reaches the neocortex. Sometimes also 35 millimeters is used, but usually 30. In children, sometimes smaller distances used because, well, the head is smaller and the brain is a bit closer to the scalp. And what we then measure is a volume. So you have to imagine that this image is, of course, in 3 dimensions. So we measure like a voxel in fMRI. And obviously, not only the brain has blood and oxygenated and deoxygenated hemoglobin, but also the skin and the skull. So what do we expect when we measure a NIRS signal? Well, the signal is very similar to what we would expect in fMRI, or what we measure in fMRI. In fMRI, we measure the BOLT response, the blood oxygenated level dependent signal. And that is a proxy of deoxygenated hemoglobin, which is, again, the blue trace in this picture. If a certain brain area becomes active, that means there's an increased metabolic demand. So there's an increase in oxygen consumption. And there's a certain phenomenon in the human brain called neurovascular coupling. And that, due to the increased neurometabolic demand, there will be an increase in blood flow that arrives just a tiny little bit later. And that leads to an increase in blood volume. And all of these effects combined lead essentially to an increase in oxygenated hemoglobin and the decrease in deoxygenated hemoglobin. Which means if a certain brain area is active and it does require oxygen, you will actually see an increase in oxygenated hemoglobin, although it consumes oxygen. I always like to explain this as a kind of protective mechanism of the brain, because a shortage of oxygen would be very dangerous for brain cells, so they would eventually die off. So the brain somehow overcompensates to be really sure that there's really no shortage of oxygen. That's roughly how you can imagine that. The hemodynamic response takes a little bit of time. So you can see on the left, the time axis goes from -5 seconds to +15 seconds. And at time 0, there was a stimulus onset. Then it takes a couple of seconds until the neurovascular coupling actually kicks in. Sometimes you can see in the first seconds that oxygenated hemoglobin actually really goes down and deoxygenated hemoglobin goes up because oxygen is consumed. But then a few seconds after that, you see the increase in blood flow. And at around 5 to 7 seconds, you really clearly see an increase in oxygenated hemoglobin and a decrease in deoxygenated hemoglobin. What we also do in NIRS is we plot the total hemoglobin signal, which is simply the sum of oxy and deoxygenated hemoglobin. It just gives you a little bit more insight. So in contrast to fMRI, we see a bit more. We see oxy and deoxygenated hemoglobin, and fMRI just sees this decrease in deoxygenated hemoglobin. And that way we have so to say, an additional control factor. So we know when an actual hemodynamic response happened in contrast to, for example, an artifact, where you would see, for example, both oxy and deoxygenated hemoglobin increase. Then you would know this is not a hemodynamic response. So how does this actually look like in real life, so in an actual experiment? So here you see a study, an actual FNIRS study. It shows the basic principle of stimulating the neocortex and then observing the hemodynamic response. So subjects had to fixate on the fixation cross in the middle, yeah, and then the left or right hemifield, so visual field, was stimulated with an alternating checkerboard pattern flashing at 8 Hz. And conditions were, of course, pseudo-randomly ordered. So on the right, you can see the hemodynamic response for for left hemifield stimulation and for right hemifield stimulation. And in the columns, you see the activation of the left occipital cortex, the right occipital cortex. And as we also know from neuroanatomy, we know that the left visual field is processed by the right occipital cortex, and the right visual field is processed by the left visual cortex. And this, you can clearly see this here. So if we stimulate the left visual hemifield, we see activation in the right occipital cortex, but no activation in the left visual cortex, and vice versa for right hemifield stimulation. So this study is let's say, a good handful of years old. So it's from 2001. It's actually from my boss. And it nicely illustrates how a NIRS signal looks like. Okay. Yeah, my PowerPoint just, I think it crashed. Okay, apologies for that. Let me quickly restart PowerPoint.
So I can see the last slide. Just restart.
Yeah. Okay, 1 second. Okay.
It's loading again. And I have the slide again like before.
Okay, great. Okay, so as I said, this study is pretty old, so it's nearly 20 years old. So, and in recent years, NIRS development has sped up tremendously, and instead of recording from a few sites only, it's now possible to have a large number of channels. And that even enables to have retinotopy mapping with a spatial resolution of a few millimeters, so sub-centimeter resolution, roughly. And that's, of course, super awesome. But unfortunately, this particular study was made with a device which looks like this. So it's a big stationary machine using glass fibers. And that's, again, impractical for studying naturalistic environments. So the study from Zeff and colleagues is about 13 years old, and the study from Eggebrecht and colleagues is about 6 years old. So it has been some time, of course. The actual devices that we now sell commercially look like this, so they are head-mounted. And you also have a lot of channels, but you don't yet have the sub-centimeter resolution. Of course, we do have commercial stationary products with which this would be possible. But obviously, if you want to go more into the naturalistic mobile direction, then you need a mobile device. But there's a very good chance that if you start writing your grant right now, that the portable devices that there are on the market will actually have even sub-centimeter resolution when your project is starting, just because all the grant schemes financing takes so long. So let me quickly summarize again what NIRS is doing. So NIRS measures the hemodynamic response. It's based on light absorption in the volume of tissue, and it returns concentration of oxygen deoxygenated hemoglobin. The advantages of the system is that it's affordable, it's portable and wearable, and it has a high focal and spatial resolution. And with this, I mean that you really measure where your optodes are located. So you don't measure as an EEG nearly everything that happens in the brain, but really just the specific location that you're measuring. NIRS has a relatively high signal-to-noise ratio, so you need only about 7 to 12 trials to get a good average out, and it's relatively invulnerable to artifacts, to movement artifacts. Of course, NIRS also has disadvantages, so you have a relatively low temporal resolution, and that is compared to EEG mostly. Compared to fMRI, we have a relatively high temporal resolution. So our NIRS devices measure with 50 to 100 Hertz, which is relatively much. And the stationary device we have can measure up to 250 Hertz, which is also a lot. And you might wonder, why do you need this high temporal resolution if you have the hemodynamic response taking a couple of seconds anyway? Well, this brings me to another disadvantage, which is that it's sensitive to systemic activation. So as I said, we also measure skin and skull, and especially on the skin, on superficial layers. There's also changes in blood flow, and that's something you measure with NIRS. But fMRI is similarly sensitive to systemic activation. So for example, there's nice videos where you can see the effect of the heartbeat in the brain. And another disadvantage is, which I also said is an advantage, is that it's sensitive to only focal neurocortical activation. So only to the location where you measure, and also only to neocortical activation. So you cannot measure deep brain regions, and that is simple physics, that the light we shine into the tissue will get absorbed. And I said that the systemic activation is actually a disadvantage. I would like to show you an example of an actual NIRS signal. So this is how a NIRS signal looks like. Again, in red, you see the oxyhemoglobin signal. In blue, you see the deoxyhemoglobin signal. And in green, you see the total hemoglobin, so the sum of the two. In this case, 0 is somewhere arbitrary, I think here. That is why green is below oxy and deoxy. So what you can nicely see here is that the signal is rich on oscillations. So you see a somewhat faster oscillation, and that is the actual heartbeat of the subject. So that's something we always record with NIRS, just because we have a high enough temporal resolution. You also see some other oscillations which are a bit slower, and these are actually related to respiration and blood pressure. So while most people say that it's a disadvantage that NIRS is sensitive to these systemic activations, I would actually say it's a big advantage, because just by measuring NIRS on the brain, you get this for free. So it's something you can use in your research. And I always wonder why most people throw that away. So we have some research projects going on where we are actually interested in finding out how to best utilize these signals, because they are there, and we do have the devices with high temporal resolution. And that is actually something that I'm not saying that because I work for the company, but it is actually one of the things that makes our system unique, because other systems don't have that. NIRS, of course, is not the only mobile neurotechnology. There's also EEG. As you might know, EEG measures neuronal responses based on the electrical activity, and you get the neural activation in microvolts. Also, EEG is affordable and portable and variable. It does have a high temporal resolution, so you usually measure at kilohertz. The disadvantage is that usually it has a relatively low spatial resolution, and that's mostly because of volume conduction, so electric field just spreads in literally no time from one location to everywhere else. And you have a relatively low signal-to-noise ratio, so you need much more trials in order to get a good trial average out. And it is relatively sensitive to artifacts. And if you now look at this list and at the NIRS list, you see that there are advantages that EEG has, which are the disadvantages of NIRS and the other way around. Plus, the principles of both devices are actually complementary. So while one is measuring hemodynamic responses, the other is measuring neuronal responses. So why not combine the two? Then you would get a more complete picture of what is happening in the brain. Both are relatively affordable, and they are actually nowadays nice integrated solutions. So, for example, g-tec has the Nautilus EEG NIRS headset, which is completely head-mounted, as you can see here on the left. This is actually all the amplifier for EEG and NIRS combined. Due to the head mounting, you're highly flexible. Of course, you can make mobile naturalistic studies, but you can also, for example, go to patient's home with this device. So it's no problem anymore to transport this from A to B. And then you can collect synchronized NIRS and EEG data. And I will give you some examples why collecting NIRS and EEG data combined is actually useful also for you if you're just recording EEG or if you're just recording NIRS up to now. Should be there. So NIRS can actually excel in command detection. So NIRS is excellent in saying whether a certain brain area is active or not active. And this is what I illustrate here with the oxygenated signal in red and the deoxygenated signal in blue. So you saw in the examples, as soon as there's stimulation, you see this increase in oxygenated hemoglobin and the decrease in deoxygenated hemoglobin. So in this study by Tomita and colleagues, they used EEG and NIRS in an SSVEP, so steady-state visual evoked potential paradigm. And you can see certain conditions, for example, on the upper left and lower right, in which classification with only EEG in blue or with EEG and NIRS in red, both is about equally good. But there are certain conditions in the upper right and the lower left, where classification with only EEG resulted actually in a high error, as you can see on the y-axis. And as you also now know, since I explained the hemodynamic response, the longer the epoch, the lower the classification error became when you include NIRS. Obviously, because the hemodynamic response takes a couple of seconds. But still, this is a good case why you want to combine NIRS with EEG, because you actually can better detect in certain conditions when the brain is active and when not. This is something that NIRS is very good in, EEG usually is not very good in. But not only for detection whether or not something has happened, it's good. You can also just combine NIRS EEG classification for paradigms that are already known. In this study, Blokland and colleagues used FNIRS and EEG to classify attempted and imagined movement in patients, in tetraplegic patients. They studied 7 patients and they investigated what the classification rate is of only FNIRS only EEG or combined EEG and FNIRS. And they did that, as I said, for attempted and imagined movement. I would like you to focus only on these columns because these are the important ones. So here they combined oxy and deoxygenated hemoglobin for classification for FNIRS. In this column, they only used EEG for classification. And in this column, they used both EEG and FNIRS. And in the left half, attempted movement, right half, imagined movement. And attempted movement, they attempted because they were tetraplegic, so they couldn't actually move. And you can nicely see that the classification accuracies in total are for the combined classification higher than for the individual modalities. And you get an increase of about 5 to 9%, sorry. But also you see for individual subjects that non-responders, for example, in the NIRS domain, if you combine EEG and FNIRS, you get a very higher classification result, but also non-responders in the EEG modality can actually get a higher classification accuracy if you combine FNIRS with EEG classification. So it might be one way to overcome a little bit the BCI illiteracy problem that we have. And I'm actually very sure that if some of you might know the Cyberthlon, and up to now only EEG devices have been used, but there's nothing saying that a combined NIRS EEG device cannot be used. So if you're interested in joining the coming Cyberthlon, which was now just moved from this autumn to some other time, please write an email and I can see what we can do for you. But I'm sure that we can make a very nice case and hopefully beat the competition with FNIRS and EEG. On top of that, the application of combined NIRS and EEG can also have a strong implication for the clinical field. In the clinic, sometimes EEG is used, but hardly ever FNIRS is used. So sometimes in the ICU, you see NIRS as a global cerebral oximeter, but that measures really a global brain oxygenation value. And also the temporal resolution usually is very low. But here in this study, they really used FNIRS, functional near-infrared spectroscopy, similar to functional magnetic resonance imaging. And you can see that the positive predictive value, they try to classify patients in a coma and distinguish those from patients who are conscious, minimally conscious, or in vegetative state. And you can nicely see that the positive predictive value was about 85% or higher, which is a classification rate they were not able to achieve with only EEG, and not with only FNIRS. So this is another nice example what it brings if you combine both EEG and NIRS together. So how does this help to resolve the issue? So, of course, wearable is a relatively new trend. So we don't have wearable devices for decades already, just for a couple of years. This can be a good opportunity for you because you can be one of the first and make a name in the field of yourself for mobile brain imaging. Of course, while wearable neurotechnology allows experiments to be taken out of the lab, it's not as easy as it now sounds, of course. So there are additional problems that you might have. The easiest thing you can do is utilize the insights from the lab experiments and make the task a little bit more naturalistic. But even if you then combine NIRS and EEG, there was a relatively recent review from Ahn in June, which concluded that the current studies lack complete integration. So they literally said that the current problem is a lack of computational approaches to feature integration and the mismatch in the recording locations between the two modalities. Now, the latter is nearly solved. So using the Nautilus NIRS EEG device, you have nearly the same location for recording. So that's nice. But still the integration of the different modalities is still a bit something we need to work on. Of course, you can treat both modalities individually, but if you integrate the two modalities, you can get a much better picture. Some of you might be familiar with EEG-informed fMRI. So if you do combined EEG and fMRI experiments, there are certain techniques to combine information from both modalities, because they are also complementary, but they have much more issues, obviously, because fMRI produces a strong magnetic field, and EEG is sensitive to electrical fields. And as you might know from physics, every magnetic field induces an electrical field. So there are huge artifacts in the EEG. And also there can be artifacts in the fMRI signal. Whereas EEG and FNIRS, they don't interact with each other on any level. So FNIRS is just light, and EEG is passive. It just measures electrical activation. So there's no interference whatsoever between the two. So you could learn from the fMRI field and use, for example, multivariate methods to make sort of EEG-informed FNIRS algorithm. Of course, you could also try to combine biophysical and neurobiological models. For example, you might know dynamic causal modeling, which is a technique to infer functional connectivity between brain regions. And that exists both for EEG and FNIRS. And both these techniques work by having an underlying neurobiological model, which means it might be possible to combine these two models into one neurobiological model and then infer functional connectivity at that level instead of on the activation level. Of course, mobile and near-EEG measurements are not without issues. So naturalistic environments have more distracting stimuli, lower signal-to-noise ratio. You will get movement artifacts, which can be both systemic but also extrinsic, which means we still need better models and better algorithms. And we might especially need adaptive algorithms. For that, we might need additional sensors. So for example, an inertial measurement unit can be used. In this study by Siddiqui and colleagues, they used a NIRS device and they used an inertial measurement unit, an IMU, which consists of 3 parts. It has an accelerometer, a gyroscope, and a magnetometer. Sometimes it's called a 9-axis accelerometer, but it's actually 3 times 3 axes. So each of these devices has 3 axes, X, Y, and Z. And then they devised an adaptive filtering algorithm. And that's actually no rocket science that they did. They just used an autoregressive model with exogenous input, which is a similar technique that is used in adaptive noise cancelling. So they just used a technique that was already there and just applied this in NIRS. This is an example of their data. So on top, you can see the NIRS data. You again can see the pulsation of the heartbeat nicely. And then the blue vertical lines are the onset of the movement. So there are 3 periods in which the participants moved. In the 2nd, 3rd, and 4th row, you see the data of the accelerometer, of the gyroscope, and of the magnetometer. And you of course, obviously can nicely see that every movement, every head movement was mirrored in the IMU data. So you can clearly see if there's an artifact in the NIRS signal, there's also an artifact in the IMU data. And they use these data just to regress out the effect on the NIRS signal. And the same principle can, of course, be used for EEG. And by just combining these different algorithms and being a bit more adaptive and a bit more aware of the motion artifacts you can transfer your lab experiments into naturalistic environments or directly start with naturalistic environments. So we get one step closer. Of course, I should emphasize that fundamental studies are still required to build a foundation for these studies. So we need to know what to look at, and we need to have a clear hypothesis. So we can still study elderly and ADHD children, but we should still learn from fundamental studies. So a couple of years ago, I wrote a review together with colleagues called Hypothesis-Driven Methods to Augment Human Cognition by Optimizing Cortical Oscillations, because cortical oscillations were the topic that I graduated in on my PhD. But the same still holds for any research that's being done. So I still strongly believe that if we want to apply neurotechnology to a naturalistic or real-life scenario, we need to look in literature what hypotheses are there and learn from the insights, and then just apply them into real life. And only then you can really find out whether the techniques work in real life. So maybe we are already in the future and we just don't know it. Maybe we just need to combine EEG and NIRS and adaptive and integrative algorithms. And then we can do already the things that we always thought can only be done in the future. So maybe we really need to start combining more modalities and utilize the complementary nature of these devices. And maybe then we can finally build a real sleep-inducing alpha rhythm generator. Who knows? I would like to thank the funding agencies that also we have, who support us in the research and development that we're doing. And I would like to thank g-tec and Christoph Guger again for inviting me and giving me and our company the platform to share our thoughts and ideas. Thanks a lot.
Thank you very much. This was a very nice talk and introduction into functional near-infrared spectroscopy and much more. We have also a lot of questions and answers, and Jörn, maybe you can click on the Q&A button and we can just start on top. So Suyata is asking, do you know any data sets for emotion recognition?
Let me think. The question is probably if they are open data sets that you can download. There are relatively few NIRS data sets at the moment available, which is something that hopefully changes in the future. So you might know about the BITS initiative to share data, and there's currently an initiative to also include NIRS. So I hope that there will be more data, but I'm not aware of any emotion paradigms that are shared.
So as usual, you can just participate in the brain-computer interface hackathon, and then you can just record emotion data yourself, and then you can analyze it. So Maya is asking, how do you measure the activity in the occipital cortex using fNIRS? Isn't it limited to the frontal cortex?
It's not actually. So you can see on this picture maybe also, I can activate the laser pointer again. Yeah, so you can see that this on top of the head cap are the optodes that we have, and they are a tiny little bit pointy. And the problem in, I don't know, some 10 years, 15 years ago was mostly that hair is absorbing a lot of the light. But you can move the hair a little bit to the side, and because the optodes are a little bit pointy, you then can make scalp contact, and then the light shines through, normally through the tissue.
And Lahav is asking, I saw that NIRS head. Can there be a NIRS and EEG electrode together in the same head?
So in theory, they can be at exactly the same position. That would require a bit more integration work, because then the actual optode holder that we have would need to have an EEG electrode. You can do that, but in practice, it's also the question whether you want that, because we use a receiver and a transmitter. So here you see, I don't know which of the two is what, but one of them is the receiver, the other transmitter. And the light goes from the transmitter to the receiver, so we actually measure in between the two. And if you now want to measure at the same location, it would make more sense to place the electrode exactly between the optodes.
And in the next talk by Gary Hirsch, you will see how the fNIRS and the EEG is mounted on the same cap to get both signals simultaneously. Then a no-name is asking, can you please explain why EEG has low spatial resolution and high temporal resolution?
Yeah, so I can start with the latter. So the high temporal resolution is obviously because what we measure in EEG is it's not the action potential, but it's more the effect of the synaptic, of the action potential on the synaptic cleft. So there's a secondary return current, but still this happens within milliseconds. So that is an activation that takes about 10 milliseconds maximally. And EEG just has a high sample frequency. So it just measures that activation. Then the spatial resolution problem is that an electric field similar to light, if you switch it on, it goes into all directions. And I always like to explain that if you take water and splash it against the wall, it also splashes into all kinds of directions. And the same is happening with electrical activity and your skull. So you have an electrical field that hits the skull and that spreads into all directions at the same time. And that's why if you measure at the occipital cortex with EEG, the activation could actually potentially be also from the frontal cortex. And there are algorithms to model that, of course, but it's still relatively low spatial resolution.
Then Christian is asking, which algorithms are you using in FNIR's EEG?
That's a very broad question. So at the moment, there's not too much integrative work done. So mostly what is done is either one of two approaches. EEG and NIRS are treated separately, and then you just look at activation in one domain, modality, activation in the other modality, and you compare the two. Sometimes multivariate methods are used, and that can be classification techniques, for example, like support vector machines or also neural networks. But there's not that much work done on combining the two. So also the combination of EEG and NIRS is it's not new, but the way it's integrated now is much better than it was before. So it's much easier to be used. So that's why there's not too much at the moment.
And David Painter from Australia is asking, thanks, Jörn. I think you are right to note the gap between lab experiments and the real world. Mobility seems like part of the solution, but how do you control the environment to measure event-related potentials and hemodynamic potentials that are time-locked to external events?
Yeah, that's a good question. For some paradigms, it's hardly possible, of course. Like for steady-state evoked potentials, it depends a lot on the attention of the subject. I think we're still really relatively far away from applying these techniques in actual real life. We still need to do much more research, especially on how to interact with distractors. So it's hard. I think it requires just more research.
Ridika is asking, can you use FNIRS EEG with high-density direct current stimulation?
Yes, that can be done. There are a couple of studies doing that. And there was also a recent review on that. It came also, I think, a couple of months ago, maybe.
Do you see any interference if you're doing the direct current stimulation in the FNIRS?
No, usually not, no. So we have, the holders that we have are basically plastic. So a bit better plastic, but still plastic, so not conductive. And there's no interference if you do it correctly. It's fully visible.
So in the EEG, you see, of course, interference because we are measuring voltage. So you have to be careful which electrodes and amplifiers you use when you do the direct current stimulation, especially if the current is getting higher and higher. Then Rabbi is asking, hello, is it possible to measure human cognitive performance using EEG and FNIRS? Is it possible? Then how can we do that and which temporal information we shall focus?
Yeah, so that's something that we are also investigating right now in a research project, how we can best do that. The most interesting brain area is probably the frontal cortex, which is also easiest because you don't have hair, so you don't need to move hair aside. That's so similar to the question that we just had about the occipital cortex.
So in the next presentation, you will see an example where we are using the strobe test for measuring cognitive performance with EEG and FNIRS.
Yeah, that's actually a perfect example. So, yeah.
I think with that, I'm ending your session. This was very nice. Thank you very much. It was a pleasure to have you here. And I hope to see you soon in one of our project meetings.
Sure, I hope to see you too.
So please stop the sharing of your screen, because this allows me to bring Gary Hirsch to the panel. I unmute Gary and ask him to share his video. Bye, Jörn.
Bye.
Now I see already Gary. I can also hear you. This is good. So please press the share screen button. Let us see your desktop. And Gary is demonstrating now how to actually measure FNIRS in the EEG with the G-Nautilus FNIRS device. And he has also a couple of slides and Simulink models to show you how to do all these tasks in real time. So welcome, and please go ahead.
Thank you. Yeah, welcome to my presentation. My name is Gary, and I will show you basically wireless EEG and FNIRS recordings, and specifically then a multimetry and a strobe experiment. Yeah, as we had before in this nice presentation of Jörn, FNIRS is a non-invasive functional method to assess brain activity. Specifically in our case, we are using near-infrared light and infrared light at 2 different wavelengths to assess the oxygenated and deoxygenated concentration values of the blood. And these concentration values provide information regarding of the activity of the underlying area. The principle, as we've already heard before, can be explained quite briefly. So the basic setup also for our device, which we have here, consists of of 4 transmitters and 1 receiver in the middle. So you always have a grid of basically 5 optodes. And currently we have the possibility to measure at 4 different locations. For each location, we can then assess concentration of deoxygenated and oxygenated blood or hemoglobin. As we've in this picture, you see basically that the extinction coefficients are, of course, depending on the wavelength and are also different for the oxygenated and deoxygenated hemoglobin. And that's also the reason why we can then distinguish with these 2 signals between the 2 concentration levels. Specifically for this product, so this also, of course, from Artemis, it's a continuous wave FNIRS. So light with, as already mentioned, a defined wavelength is applied into the tissue and region of interest. And depending on the tissue, you have a specific absorption and scattering happening. And the outcoming intensity change is then again acquired. This formula you see down here is basically the modified Lambert's law, which also takes into account the scattering behavior. And in the end, it will then provide the relative oxygenated and deoxygenated hemoglobin levels. And this is also then the signal we are using for the later proposed algorithms. Just as an example, here are 2 exemplary signals of HBO and HBR. As you can see here, so the red one is the oxygenated one, blue one is the deoxygenated one. They're more or less so this is actually in response after a certain task without any filtering. And you can see that there is a high frequency behavior, which is the pulsatile wave. And then we have a low frequency response, which is coming from the actually activation of the area. And in that case, it's in the range of, so you have a peak after 7 seconds of the task onset. In that case, it was multimetry. As you can imagine, if the levels of oxygenated hemoglobin are rising, the relative levels of the deoxygenated hemoglobin are dropping. Yeah, there you have a more averaged and also filtered response of oxygenated hemoglobin. In that case, there was at second 0, there was the task onset. In our case, it was to imagine a certain movement, specifically either left or right hand grasping. Then you have quite often this initial dip. And after 7 seconds, you basically reach the peak level of the HBO response. And after this peak level, there is also a certain time. So in that case, the task lasted for 10 seconds. So the subject stopped thinking of the specific task after 10 seconds, and then it takes some time to come back to a baseline level. These values you see here are not really representative We are using continuous wave FNIRs, so they're very relative, which will also then come back later in my algorithm. So we are basically only looking for relative signal changes. So in our case, you can't directly assess the oxygenated or oxygenation level of your blood, for instance, in percent. Here's the HBR response. Basically, as I said, we have a negative correlation, so the relative concentrations are dropping after the task onset. Then, as you might have already guessed, this cap has more than just the 10 optodes of the FNIRs. There you have also, in that case, a 16-channel EEG, the Nautilus attached. So we're also simultaneously measuring the EEG signal. And here just exemplary EEG, of course, with much higher frequency components. So why are we using both? I think my previous speaker already explained it quite in detail. So we can basically increase, in many cases, performance robustness. We can estimate the neurovascular coupling. That's actually the connections between the neural firing, which then manifests itself as an electric activity, and vascular activity, which is coming from the increased or decreased demand for oxygen. And of course, it's a relatively low-cost complement to an already existing EEG system. So very specific for our devices, as I've already mentioned, we're using the g-Nautilus. In my case, it's a 16-channel device. It's possible to use up to 64 channels. We have 24-bit of resolution, and the sampling frequency goes up to 500 Hz. The FNIRs is an 8-channel device. We have a sampling rate of up to 50 Hz, and the data or the light is applied at two different wavelengths, so 760 nanometers and 850 nanometers. There you have a maybe more visible depiction of the hybrid system. As you can see here, we have the electrodes spread over the cap, and then we have the holder rings, which are also attached to a certain, I think it's out of rubber placeholder, which keeps the certain distance, which is required between the receivers and transmitters. And in this holder rings, you can then plug in the receivers and transmitters, so the optodes. For our systems, we have two different optodes, the low power and the high power ones, depending on the possible obstructions you encounter. So a main one is basically hair, and also on the region you're measuring, and then other stuff like if the signal is saturated, or if you have any other use cases, you then basically choose between the low power and high power optodes. Yes, then for our experiment, so this might be a bit for the future, we have then also a signal quality assessment, which is EEG based. It's quite simple. So we are basically saying, okay, we have a common reference signal, and if you have artifacts, they should be visible in all channels. So there we have quite a sensitive algorithm to detect it, quite simple algorithm. And for the FNIRs, we have, especially for the Simulink model, more, I would say, sophisticated algorithm. This one is based on the full cross correlation. Then we normalize the cross correlation. We calculate the zero cross correlation to get we call it then skull coupling index. Or the second approach is to actually perform a spectral power estimation, and then we have the extended SCI. Basic idea behind this algorithm is to detect if the pulsatile waves are visible or if they exist in the signal. And for both cases, so for the oxygenated and deoxygenated hemoglobin concentration levels. And if they're visible, we have a certain chance, or we can be sure that we have a nice coupling between the optodes and the skin. And especially later, when we have the live measuring, I will go more into detail why it's important, or why it's tricky to have a nice skin coupling. Yeah, as I already mentioned, I will show you basically 2 experiments which are based on the FNIRS EEG hybrid. So first we are going to start with a multi-imagery experiment and then with a strobe experiment. Of course, for the 2 experiments, as you might already know, it is beneficial to have different setups for the electrodes and optodes. And just to give you a brief overview, so the image on my left-hand side is for the multi-imagery experiment. There we focus mainly on the motor cortex, of course. Also, in our case, the 8 FNIRS optodes, or 10 FNIRS optodes are placed over the motor cortex. And for the strobe experiment, as we want to basically assess the mental activity of the subject, we are focusing on the frontal lobe. So we put the optodes and the placeholders in the frontal area, so it will be in this range, because this cortex area is linked to abstract or abstract thinking, and also to basically focusing on tasks. So in general, the BCI we are going to show are same principles regardless of the signal type we are measuring. We are getting first the brain activity, compute the signals, feed it into a feedback system, which is especially crucial for a multi-imagery experiment, then provide online feedback for the subject. And secondly, of course, you can also control a physical device. In that case, it was basically just a feedback system we controlled, but then you can also use it to interact with the actual real world. We have certain processing steps, so they are the same for both experiments because the underlying brain-computer interface is more or less identical, only some minor differences. First, we have the data acquisition. Then we are performing a quality assessment. Then we have some pre-processing steps, which range for the EEG from simple bandpass filtering, notch filtering, then also spatial filtering. So for the EEG part, we are using the CSP, spatial filter analysis. And for the FNIRS, we also pre-filter it. Basically, we filter everything, or we filter out everything above 0.3 Hz, because these are signal components which are normally not informative for the actually brain activities which come from, for instance, motor imagery or certain levels of concentrations. Finally, we feed all the extracted features into a classifier. In our case, we are using the linear discriminant analysis. From the individual linear discriminant analyses, we then feed the score values into a meta classifier and then provide final feedback, which basically takes into account all 3 types. I say 3 types because we have the EEG, the oxygenated and the deoxygenated hemoglobin information. And based on the final decision of all 3, we then provide feedback for the subject. Here we have it a bit more graphically. As I said, we have data, we filter it. The upper branch is for the EEG. We apply the CSP filter. We get the EEG features. We downsample. This has actually only performance reasons. We feed it into the classifier. We get a prediction for the EEG, so a score value. Then for the FNIRS, we filtered, we downsampled it before. We make a baseline removal. As I said, we have continuous FNIRS, so we don't really have absolute values of any kind. With baseline removal, I mean that we have, for instance, we have a task onset for the motor imagery. And for each task onset, since it's a paced experiment, we subtract for each channel the mean value of the previous 3 seconds from the ongoing signal during the whole task. From this baseline corrected signal, we extract then features via a sliding window. As we might have heard before in the previous presentation, FNIRS signals tend to have a way higher signal-to-noise ratio compared to EEG. signals. So the features we are extracting are actually rather simple. In our case, it's basically the mean and slope value over a certain window size. And we do this, as I've mentioned, for the oxygenated and deoxygenated hemoglobin signals. And then we feed the HBO features and the HBr features in their respective classifiers. We again get score values for each of the classifiers. And then all the score values are going to the meta classifier. As you can see here, we then have basically 3 score values. They go into the meta classifier, and the meta classifier is then providing a final prediction. So then, I would like to start with the MI experiment. And for that, I have here my colleague. We'll now swap places.
Hello to everybody.
We will start it directly from the new G suite. There we select the g-hysys package, open it. Then we wait a few seconds. I might readjust the camera. Hope not destroy my measuring setup. So that you then can also see the challenges of mounting FNIRS. As you can see, my laptop is quite relaxed, so this might take some time. But finally, Simulink is opening and MATLAB. Before we have here again the cap. And in our case, since it's a combination of the Nautilus itself and the Artemis FNIRS, we have the base station for the Nautilus, which is already plugged into the laptop. I think I dropped something. And the Nautilus pairing is quite straightforward. Just keep the power button on the amplifier itself pressed. Perfect, Simulink is open. Now we have to connect the FNIRS device, put in the battery, open Bluetooth devices to pair it. Perfect. Add a device, and there we have it, the Octa 16096. And we are connecting. So both amplifiers are connected. We can now select the respective model directly from the Simulink start page. There we have the FNIRS section. We have the possibility to simply check out the amplifier itself with a short demo. So this is just recording. Then we have the multi-imagery experiment. The multi-imagery experiment for offline data, which is previously recorded, and also to check out the individual steps before you actually make a record. Then we have the strobe experiment for new data. And then we have the strobe experiment for offline data. Good. But we are starting with the multi-imagery experiment. Before we start with the multi-imagery experiment, I give you a brief idea how it will look like. So we basically have our subject sitting in front of the PC. This experiment is also we are also using FES to apply additional stimuli during the first phase, which we're using to record data. Then the FES is basically always applied. And during the second phase, the FES is only applied for the case of positive feedback. Additionally to the FES devices, we also have a 3D avatar, which is indicating the movement of the desired arm. So in our case, we have the left and right hand grasping. And the avatar will also only move in the second run then if there is a correct classification. Just an overview of the whole experiment. So as I said, we have 2 runs. First run is for calibrating the classifier. Second run is for then evaluating it online. And we have here a pre-rest time of 30 seconds. It's necessary to also get a certain baseline for the FNES. Then we have an instruction and task block. The sequence is randomized, so it's either left or right. And then we have a rest time of 15 seconds. And it's quite long, but it's also necessary to get the FNES response down to a baseline. And now we can go back to the model and open it. And I can slowly start to mount the cap. Mounting normally takes quite some time because you have to not only gel the EEG, but we also have to mount the FNES optodes. So the cap mounting is quite straightforward. You have to apply if you look at the top, you have the CZ, which is often used as a reference for the correct mounting of the cap. It's festpasst. And now comes the more tricky part. So as a little tip, it's quite handy if you, here are the 2 phases. We first select the calibration phase, press apply. During the calibration phase, we then also can additionally define where we want to save the data, where we want to save the result, which is in that case just empty because there is no actual classification performed. And we can also modify the paradigm, which is here our motor imagery paradigm presenter. In that case, I created a big pre-rest time so that I can check the signals before we actually start it. We have quite a high number of trials. We have 50 trials. And in this case, we also selected that we have after 50 trials, after 20 trials, a break. Finally, you can also select here the sequence of the presentation. So you can either say default, which is in that case the standard sequence of left and right hand grasping. We can randomize it, or we can also custom it and then basically enter any sequence we want. So you can change a lot here. Okay. So now also start the model. We also have here the 2 FES devices in the moment they are commented out. But let's, I forgot to configure the amplifier, so I will get an error now. They can start by now with the gelling of the electrodes. Always slightly twist it, apply the gel, and then slowly remove the syringe from the scalp until the gel is reaching the top of the, in our case we have Scarabeo electrodes, the top of the electrodes. Okay. Yeah, it's important to avoid any bubbles, but it's best to check it out then with the scope if you have bad signals. And model started. Sorry. And the last 3 electrodes, and then of course the reference electrode for the earlobe. Oops, 2. As you can see, the model is already running. We have probably see the display. Which will later show the instructions for the subject. Oops. Bit complicated with the camera. Okay, I'm not sure if, yeah, I think as I said before, I forgot to set up the g-Nautilus. Just double click, then all available devices will be listed, or if it's only one, then the configuration should open automatically. Yes. In our case, we have here all 16 channels selected. We have a bandpass filter from 0.1 to 30 Hertz and a notch filter in Europe, so 50 Hertz notch filter. Press apply. And it's saved. That is not a device number. For the FNIRS, we have here the possibility to select the sampling rate. I said before that it's actually sampling with 50 Hertz, but it's upsampled so that we have a simultaneous data acquisition with our Nautilus, for instance. And there we can also upsample it to 500 Hertz. Here we have the Bluetooth address, which is written on the device itself. Of course, it has to match. And there we can add the differential path length factor, which is taking into account the actually physiological condition of the area we're looking at. You can also calculate differential path length factor, and then it takes into account the age of your subject. But for our experiments, it's not that important to make it that precisely. So we can just say apply. Yeah, as output, we have the optical densities and the concentration values. Concentration values are then the results of the modified Lambert's law based on the optical densities. And our BCI is then actually using the concentration levels. Good. Good. So while I start the model, I can show you how to properly mount the optodes. Optodes are a bit tricky. It highly depends on the subject. So as I've shown you before, we have take the camera briefly. We have this group of 5, 4 transmitters, 1 receiver in the middle. And yeah, probably the first problem you will encounter if you ever use this is hair. So there's quite a simple solution. Just remove the optode, use some sort. In my case, I use these bent plastic syringes. You can also use a Q-tip. and then remove the hair beneath it until the scalp is visible. Then you plug it in. You can also see here that it's already emitting light. Probably can see it. And just press it in firmly, but not too firm, because these things can get uncomfortable if you have a long experiment. Just repeating for all 10 optodes. The one in the middle, quite important. If this one is bad, all 4 signals are bad. Yeah, as I said before, we have the low-end high-power optodes. For this experiment, I'm using the high-power optode. I think I have here. So, the second side, left hemisphere. And it's nearly done. Then we can check out the signals. We have here 3 scopes. The first one is for the EEG. So we're applying the correct range. Yeah, for instance, -50 to +50 microvolts. And you can see that it's looking quite nice. Let's see if I can load the configuration. Because we have we have the signal quality checker connected. The interfaces. Should work for both. And loaded file contained no usable. Okay, I think I have to adapt it. Yeah, anyways, for the EEG, you can make some simple tests. For instance, if you could blink, the ocular artifact should be visible. Then you can also check with clenching the teeth if the data acquisition is in real time. And when you close the teeth, alpha wave should be visible.
Not for me.
Depends on the subject. For some, it's quite visible. For some, not. Then we can check out the FNS configurator. Yeah, so it's best to increase it a bit, let's say to 15 seconds. As you can see clearly, we have so we always have a group of 2. So the first 2 channels correspond to the first transmitter. The second 2, so 3 and 4, correspond to the second one. First one is always the oxygenated hemoglobin, second one the deoxygenated one. As you can see, especially for the oxygenated hemoglobin, we have a higher signal-to-noise ratio, and the positive wave is quite visible. And yeah, for now, we will just leave it. For instance, if you have very bad signal-to-noise ratio, especially for the HBR, it is beneficial to then actually fix it by removing any obstructions. In that case, it's basically hair, probably. Good, now we have checked this one. Let's assume that the signals are perfect for our experiment. We can additionally add the FES devices, but I will leave that for now. Otherwise, we have a bit of a time issue, I'm afraid. In the end, you can just comment them out if you don't want to use them. And then we just need to start the oops, sorry, wrong. We just have to start the avatar. Yeah, the intention is that we have a more intuitive instruction and then later also feedback for the subject. Windows is making stuff. And yeah, so model has stopped. We reduced the pre-rest time to 30 seconds. And now the experiment is starting. The subject is instructed to move as little as possible. Also sit comfortable because this experiment takes some time. Normally one run takes 20 minutes, but we will not be able to do that because then my time slot is over. And during the calibration run, as I said before, the data is just collected and used for the classifier training. We can turn the camera a bit. Oops. So we have here the display. Put it here. The data is acquiring. We place the avatar here. You can also expand it to the maximum. And what you see in the background is actually the online calculation of the accuracy, which is not done in this run. And then the subject is instructed to do same as the two hands. So we always have the minus. In that case, we have R for right hand grasping. It should just be imagination, so no actual performance. And if these signs are switching to plus, then the subject should perform imagination. The minus indicates that the trial or the trial is over, and then we have the 15 seconds of rest. Quite long, but this is quite important for the FNIS itself. Normally, so after 50 trials, this would be done. Then it is stored, and we can train the classifier. We have a batch file for that normally. But I will now try to show you a simulation, how it then would look like after the classifier is trained, and how the online classification would work. For that, I'm now using the offline model. We can close this avatar. Okay, thanks. So if you could move back to then I will show briefly thanks a lot for participating. So let's see what is opened. We can close this one. And there we have the offline model. For the offline model, we select here the acquired data. So this is, can open the file explorer. Then the new Simulink release, in the new HYSYS release, we have it program files, then g-HYSYS, g-sensor FNIS. We have here the test data, and there we have a training and test run. So you could actually use the training run to train the classifier for yourself. We say that it's already trained and it's already loaded. We select the test run, press apply. Oops. Press apply. And then we additionally have to load the correct weight vector for the spatial filtering. As I said, quite relaxed laptop. And it's a bit in the way. G-sensor F-nears, test data, and we have here the weight vector. And it's loaded. And now we should be able to see how the online run would look like. So we press run. It's compiling. If all runs accordingly, it should also be a bit accelerated because we are now in the simulation, so you can see the whole experiment, which normally lasts 20 minutes in a few seconds. So the online accuracy plot is opening. And we're in already 20 seconds. 23, 30. Yeah, and we have the first results. So this would be the first trial. We have the immediate accuracy values. Then the second, and so on. So I just keep that running for some time. Normally you see after, let's say, 20 trials, if the subject is performing well. We have here 4 traces. The yellow one is for the EEG, the red one is for the HBO-based classification, the blue one is for the HBR-based classification, and the purple one is for the overall or meta classification. Okay, perfect. As you can see, the traces are becoming less random. And in the end, so for this test data I'm using, I think the meta classifier will reach around 90% for that case. Yeah, at second 0, we have the task onset. And at second, or in this case, it's called 100, so that's a bit wrong, we have the actual task end. Yeah, if you keep the bit running a bit longer, you will then also see that the EEG is in general a bit faster. The responses are faster, and also the classifier can classify the signal faster. Okay, so I think I have now to stop the multi-imagery experiment so that we can have a brief look into the strop experiment. For the strop experiment, normally you have to whoops, switch the camera. For the strop experiment, you normally have to apply a different configuration for both the EEG and FNIRS optos and electrodes. But we will just skip it for now. We close the model. We don't want to save it. So briefly before we show that, we can go through the, yeah, there you have before we have that, we have here an example of the different responses. So they are respective to the locations of the oxygenated end of the 8 optodes. And you can see here that the responses are different for the left-hand grasp and the right-hand grasp for multi-imagery. And that's also the base for our classification. We also tested it on, in our case, we evaluated it on 6 different subjects. So what's the key idea you should take from here? In the end, a combination of all three modalities outperformed each individual one. And in the end, we reached for our 6 subjects a peak accuracy of 80%. So, and this is just for the online runs with feedback. They have a bit more detailed results. You can basically see this the same as in the visual depiction, but just with a bit more numbers. But I will skip that, otherwise it will get a bit tight with the time. And yeah, now we're coming to the strobe experiment. Strobe experiment, for those of you who don't know what it is, the idea is that we basically mix the written color with the color of the word itself. So if we go to the last one, we have here written green and red, and the subject is supposed to think of red. And yeah, a whole array of such words is presented to him. And for the second class we are classifying against, the subject just has to sit idle. So we really want to see if there is an activation difference between doing nothing or doing as less as possible and compared to actual activation. In our case, we use the strobe experiment. In theory, there are many possibilities like mathematics. The setup is quite identical. Only thing, we don't have feedback devices via FES. The strobe experiment itself, as I said before, we have the strobe experiment against a rest state. In our case, we have 40 trials, and the instruction and also the post-task phase or duration is identical. Yeah, now we're coming to the strobe experiment. The strobe experiment is also here. So in the Simulink front page, just select it. For the strobe experiment, we are using the paradigm presenter. I can show you in a second how this looks like. So again, we have to set up our amplifiers. We think there's one already open. Let's close this one before. I think it's not connected anymore. Yes. Is the FNU still running? Nice, great. Now it should find it, ideally. And there it is. We have the 16 channels. We have the configuration, basically identical to the multi-imagery experiment. We have the FNUs, also identical. And there we have the paradigm presenter. For the paradigm presenter, you can create your own paradigms, write it in XML. There already the think patient window pops up. We can select the paradigm. It's called My Paradigm XML. Apply. And ideally this should have been it. So normally we also here, the signal processing, there it is. The paradigm presenter is always in the front, so it's a bit tricky. I start with the calibration phase in that case, and then we should be able to press run. Okay, this takes some time until it's compiled. And then it's simply the strobe experiment is presented to the subject. Exactly. So before we again have this relax phase, we want to go back to a baseline. after a certain period. I'll just make it small. Then the task will start. Resize it a bit, then I can proceed with my presentation. Yes, so I think all of it should be visible now. We also validated the strobe experiment with 6 different subjects. In that case, so there we can see the example of the strobe. We have a 10 by 10 grid, and the subject is supposed to really only read it out in their mind. So we don't classify the artifacts due to jaw movement, and then you have the rest phase. And this is repeated between strobe test and idle state for 40 times. Trained on this one, repeated a second time online. Then you also have the online accuracy calculation. And the online accuracy calculation, so in that case for 6 subjects, is depicted here. You can see that again, the key idea is that the meta classifier outperformed the individual classifiers. And there we have a more detailed depiction of the accuracies, just a plot, again, segmented in 10 slots during the task. And you can see that we have the maximum accuracy was reached over all 6 subjects after 7 to 8 seconds after the task onset. And for both classes, an average accuracy, so they were stratified equally. We reached 83%, for class 0, 86, and for class 1, 81. I think class 0 was the strobe experiment itself. And yeah, so that's it. So in the end, we have successfully shown that we can facilitate the proposed hybrid BCI for both experiment strobes and motor imagery. And yeah, finally a recap. So we have G-nautilus FNIRS, we have up to 64 channels of EEG, 8 channels of FNIRS at 2 wavelengths. We have HBO, HBR. We can acquire hemodynamic responses. We can investigate the neurovascular coupling. We have clearly seen a robustness and accuracy improvement. And there, of course, is a multitude of future BCI applications for such a setup. And I would say thanks. That's it from the presentation. And thank you for watching and listening.
So thank you very much for the nice presentation. It's good to see it in real time, how EEG and the FNIRS are used at the same time. We have also a couple of questions, like in BCI processing step, what does quality assessment include?
So the quality assessment, which unfortunately I couldn't show live, signal quality assessment, we have firstly the one for the EEG, where we take the average logarithmic band variance or band power over all channels and for each channel individually. Based on that, we can then detect especially movement artifacts and heavy outliers, but also if we have a loss of signal, because then it's basically going to a very small value. For that, we are removing bad channels, or we can at least distinguish bad channels from the good ones. It's especially important for the later CSP calculation to remove any artifact contained contaminated trials. And more interesting, probably for the FNIRS, we have the quality assessment with, according to a paper of, I think I forgot his name, but or the name of the group, but they proposed this one to basically focus on the heartbeat, which should be visible in the FNIRS. And if the heartbeat is not visible, it's a good indication that you have a bad skin coupling. And if you have a bad skin coupling, then you're not really measuring well the underlying vascular activity of the region you're observing.
Okay, then Nicolas is saying, I see the advantages of running both FNIRS and EEG to collect more accurate data, but is there any negative aspect of using them simultaneously?
Of course, you have a second device, so it's a more complicated setup. For the subject, it's a bit heavier weight-wise, But otherwise, if you go especially for the paradigms itself, you just have to consider that you're also using FNIRs, meaning that you have to adapt task durations and rest durations. So I don't know if you're familiar with multi-imagery based on EEG, but there the rest time is way shorter. You can, especially I would say temporarily, you have some limitations because you're using FNIRs.
But there's no bad interference between the FNIRs and the EEG.
No, not.
Then Martin is saying, hello, how important is the baseline removal? Should we do it all the time?
The baseline removal is very important because you have, as I said, with the continuous wave approach, we are only measuring the concentrations relatively, so there are no absolute values. And the normal or healthy physiology of a human just implies that you have, for instance, changes in blood pressure overall, or that you also have vascular changes which are not really related to a certain task. And if you don't consider them, then it's very likely that you basically lose the information you're looking for. And that's then also important to, in our case, since it's a paced experiment, it's the approach that you always put the HBO and HBR concentrations to a respective baseline. In our case, we just use the one right before the task. And then you have really a relative change of the two signal types, which are with a very high probability linked to the task you are performing.
Then we get the comment baseline subtraction is done in 3 seconds. Why is it so long? Neurons show the activity in approximately 200 milliseconds from the stimuli.
You could probably reduce the baseline window. So the baseline is done for the FNIRs. In general, the response of FNIRs is longer. So even if a neuron activity is very short, you can, wait a second, also see here that the response of FNIRs is quite delayed. And in general, we found out that in our case, really a 3-second window to average these HBO or HBR signals is a good way to have a certain baseline window before it. But yeah, you could play around a bit, maybe make it shorter, maybe make it longer. But the 200 milliseconds basically only applies for the neural activity, but the vascular activity is then a bit different.
And Anatoly is asking if you could do the baseline removal with a sliding window.
You could maybe do it with a delayed one. But in our case, it was just more or less offered since we have a paced experiment that we make it at a fixed point for each task. But might be possible to. I was also thinking to more or less do it with a bit of a common reference approach, which we might know from the EEG. Should be possible, especially for the multi-imagery, because you have 2 hemispheres and they're reacting differently. And then you could more or less acquire a common reference for both, and then you would see in one hemisphere for a specific task a different response. But I think there are many possibilities to work on the baseline correction itself.
Prema is asking, why do you plot the brain-computer interface accuracy versus time, and what's the duration of one epoch?
Of course. So let's go here, for instance, we have the multi-imagery experiment. I think I've explained it not very well. What we see here are 20 seconds. We have the accuracy values. We have the significance or up from where the accuracies are significant and not just random. Previously, the white one is basically the pre-task period. Then we have the blue one, which corresponds to the instruction window. It was 2 seconds. And then we have the red area, which lasts for 10 seconds. This is the actual task range. And we're plotting the accuracy. It's the average accuracy over all 50 trials in the online evaluation over the time. And there you can see that we have that HBO and HBR, that the accuracies are rising a bit or increasing a bit later, while the EEG, except for the 2 subjects here, they are quite instantaneous. So you see that the classifier, the classifier, we have only a single classifier, and there we have more or less the time variant accuracy. So at what point can we distinguish between the 2 classes?
Okay, and the last question is, what's the relation between training and testing time? So how long do you train and how long do you test for these experiments?
In our case, they were identical. So for the training, we had 50 trials, which equals, if you consider the pre-rest time, the task time, the post-rest time, etc., and also the breaks in between, to 20 minutes. And then the second round was also 50 trials with 20 minutes. Strobe experiment was a bit shorter because we assumed that, and also we tested it, that it's just easier for the subject to perform. Multimetry, if you do it the first time, is a bit tricky.
Okay, thank you very much. I think
Welcome.
this was the biggest audience that Gary ever had. So we have almost 1,300 people registered for the summer school, which is again very nice. Thank you very much, Gary, for the nice presentation.
Okay. Thank you.
And please stop your sharing of the screen so that I can invite Oren. And I ask him also to start his video.
I'm trying. A second.
Good morning, Oren, or good afternoon, actually, already.
There's share. I have it. Okay, thanks. Bye.
Bye. Oren, can you hear us?
I can hear you. Yes.
I see you, I hear you, and your presentation is
I can see my
loading.
screen.
So Oren comes from Israel. He is one of the most famous BCI researchers over there, doing a lot of work for many years. And he is also in the Negev. So if you get the chance to visit Israel, visit Oren, and he will show you this nice desert.
Right.
Okay, so welcome, and I'm looking forward to your presentation.
Thank you very much, Christoph, and thank you for inviting me for this great summer school. So yeah, indeed, I'm from Israel, from Ben Gurion University. My background briefly is from physics and computational neuroscience, but I really wanted my lab to do some experimental work, and we got into brain-computer interfaces and other work, mainly with EEG. So the goal of today for me is to share with you some of the work that we do in our lab and give you guidelines and tips for constructing biomarkers based on brain activities. I'll focus on EEG and a little bit MEG at the end, but it's very general and relevant to other modalities as well. And I will do that just by telling you about some ongoing work in my lab. So the outline of the talk, I'll start just for the motivation with some project we did with motor imagery BCI, and motivate that BCI is actually a long-term skill acquisition. And then I'll discuss this issue of skill acquisition and cognitive workload. It's a loaded concept, which we will discuss. And the emphasis here will be on using simple spectral features from the power spectrum of the EEG in combination with machine learning to learn about cognitive workload and skill acquisition. It's not a complete work, but I'll show you what we do. Of course, other people in the world are also working on these kind of things too. And then I'll switch gears, and the second part of the talk, I'll talk about critical brain dynamics. Of course, to give an intro and explain what that is. It's like a theory of how the brain works, how the cortex works. It's an interesting concept, and I'll show how how some measures of brain activity can be derived from this theory, from the theoretical idea, and it would be useful as biomarkers mainly for brain disorders. So that's the plan, at least. So here's the story of a project that we did in the past few years and was published recently. And it's around this issue of co-adaptive learning. You know that BCIs involve mutual learning. You've heard this probably throughout the last couple of days. We know that the user has to adapt his or her brain activity, but also the machine. There's a machine learning algorithm that learns to decode brain activity. And these two things happen simultaneously. And I was also interested in what's the interaction between these two learning processes and what's the relative contribution? Who contributes more, the human or the machine? And what happens from day to day? So if you've seen on the first day the talk of Lee Miller, that was really interesting. He talked a lot about that in the context of neurons and multi-electrode arrays in monkeys. So it's also interesting to see what happens in EEG in the long term and have some control for that. So here's the experimental design that we had. We had two groups. Each one did this experiment for 4 days. So they did some 4 consecutive days, motor imagery experiment. In the control group, the classifier was fixed after day 1. At the end of day 1, And then for days 2, 3, 4, they had the same classifier. So if they got better, it was only because they adapted their brain and improved their representation, let's say. The experimental group, we allowed the classifier to adapt after every block. And so they could both, improve the representation, and the classifier adapted itself to the brain. So what would happen? What would be the relative contribution of the human and the machine? We wanted to kind of disentangle these contributions using this experimental design. We had 18 subjects that were naive to the BCI, 9 in the control group, 9 in the experimental group. And it's important also to say that the first day was the same for both groups. So we used a very simple motor imagery setting, because there are various ways to do motor imagery decoding. We use the GUSBM. It has 16 channels. We use 10 of them in the Laplacian configuration, which means that we take the central channel and we subtract the 4 channels around it, the mean of the 4 channels. From the central one, it's a special filter that improves the signal-to-noise ratio. And then we extract simply the alpha and the beta features from each side. So we have 4 features. And then we use a simple LDA, linear discriminant analysis classifier, to decode. So that was basically the idea. We use a video game, so it's more engaging. There was a spaceship that flies into space, and then when you imagine right hand or left hand, there's the laser beams that goes to the right or to the left. And there are enemy spaceships that appear on the right or on the left, and you have to destroy them. That was the game. We also extracted subject-specific features. So on the first day, the first block, we trained many classifiers, and we looked for the optimal central frequency in each band and the optimal time point in each trial. So in each trial, which lasts a few seconds, what was the time point that allowed us to get the optimal decoding from each subject? And that was used for the rest of the experiment. And we used the simple LDA. It was important for us to use like 2 channels in LDA, so we can really understand the difference between the human learning and the machine learning, and use a very complex setting with, for instance, common spatial patterns. So the classifier output, as I said, was just, it controlled the direction and the length of a laser beam on the screen. So that was the setting. And how it would look like every day, they came for 4 blocks. The first one on the first day was 8 minutes, and it had no feedback. And then we calibrated the classifier, and then the next blocks, they had already feedback. And at the end of the first day, that was the classifier that remained fixed for the control group. For the experimental group, it kept on changing on days 2 to 4. So in each trial, there was just a spaceship that appeared either on the left on the screen, and the subject, if the trial lasted between 5 and 10 seconds, and the subject just had to imagine and destroy the spaceship. So if you were quick, you would move on to the next trial and get more points. The important thing is that we found this significant difference between the 2 groups. And it wasn't that both of them got better, but the experimental group got even better. It's interesting. The control group actually deteriorated. They got worse from day to day. So the fact that we did not adapt the classifier meant that on average, they could not get better. Some of them did get better, so it's important to know that some can get the skill and improve even when the classifier does not change. But for most of them, it was really terrible. They got worse from day to day. The experimental group, on the other hand, showed an improvement in performance on average. So that's what you see in this group. This is a trial time, as you, on the x-axis. These are means over the groups, and you can see this is kind of the performance of the classifier as a function of time at the beginning of the experiment, and this is at the end after 4 days, and this is the improvement, the change in the accuracy. So you can see in the experimental group there was a substantial change, whereas there was no change, and effectively they got worse. It's hard to see it from here, but for the control group, they got worse. But the important thing is that there's a lot of variability among individuals. So this is what you see here is time, but these are blocks along the 4 days. So if you look at, only the last 3 days, 2, 3, and 4. So there were 12 blocks, and you can see that these subjects kind of stays approximately the same, or this one got worse, this one got a little bit better at the end relative to the beginning. But you can see that subjects here, for instance, this one and this one, they really got better, but in a very different manner. This one got better only at the end, this one got better immediately, and then kind of remained very, very good. So how do you know if they actually acquire the skill? We know that it's important to adapt the classifier, but still you can see that the way they get better is different. What would happen if I would continue the experiment for a few more days? Maybe this one already saturated after a few days, and it doesn't need me to continue the experiment. But for this guy, maybe it's better to continue, and it's important to see if he would saturate it. Okay. So here are some conclusions that will motivate this part of the talk. So we know that co-adaptation of the classifier is a prerequisite for subject improvement in this multi-day motor imagery BCI task. Of course, other labs have found it, but it was important for me to do some controlled experiment and know that it's what would be the quantitative effect compared to a control group. So it was important we had subject-specific features, adequate adaptation protocol, and this engaging training them. All of them were important factors, but still it wasn't enough if we did not adapt the classifier. Now, importantly, what we saw in this experiment, I did not show all the graph, you can see it in the paper, but we found that the control group deteriorated all the time, between days and within days. The experimental group, they improved within days, but there was some slight deterioration between days. So every day they begin slightly worse than the next day, but then they get better, than the previous day, but then they get better. So it's interesting, but it seems that the within-day improvement that we see in the experimental group is related to probably that they could compensate for day-to-day variability. They could explore various mental strategies, because if they change their representation, the classifier would adapt. And on the other hand, the control group, if something doesn't work, it frustrates. So they kind of lose the engagement, and that's why maybe they get worse. An important thing is this higher inter-subject variability. So suppose we would like to monitor the effect of skill acquisition. You know, if subjects already got the skill and they are saturated, or if they're not, if they did not acquire the skill, we need to continue the experiment. So long-term BCI training, for example, like you would do in long rehab with BCI after stroke, it can be considered as a skill acquisition process. And how do we know in general? Not just in BCI, also in general skill acquisition of, for instance, playing instruments, video games, and other things. If a subject acquired the skill, can the subject move on to a higher difficulty level in a video game, for example? What's the optimal interval between training sessions for skill maintenance? If you look in the literature about skill acquisition, it's associated with this idea of automaticity. As we acquire a skill, we get better. So it's also associated with improved task performance, and we also become automatic doing the task. So like driving, when we first start driving, we're very stressed and we need a lot of cognitive load for this task, but then gradually we become automatic in driving. So there is this concept of cognitive workload, and it tries to capture this notion, this idea that you become automatic, and also you need fewer resources probably as you can become better. So high workload is associated with difficult tasks that require more resources. It's important to know that there is no consensus definition of this cognitive workload. It's a very loaded term. So what people do is just kind of effective definitions. This is what I'm going to show you next. So you have to translate it into some practical working definition when you want to work with this concept. So an important idea here is that when you perform certain tasks and you acquire the skill, you can really do things that could otherwise not be done. For example, when you play on a piano or in a guitar piece, the player doesn't think about the next note. He just plays it continuously. You cannot really think. It becomes automatic, and you can exceed, in a sense, the input-output speed limits that would otherwise be if you would do everything consciously. And similar for a skilled motorbiker, a skilled mountain biker, or a pilot. In all these conditions, you have to act very quickly, and you don't really think. So what happens during this skill acquisition? We started, so the idea was to monitor cognitive workload and see if cognitive workload goes down as you acquire skill. This is what we are looking for. We're not there yet, but this is the reasoning. We started with this idea of cognitive workload first in a simple setting, which is not really skill acquisition, just to see if we can predict the difficulty of a task that the subject is doing. So we use this famous intelligence test, which is called the Raven test. So the Raven test has many questions of this kind. You have a 3x3 array of shapes, and you need to guess what would be this missing shape from here. So this is a very simple question. You can understand the regularity along the rows, the columns, and figure out that it's probably going to be 8, right, here. Other puzzles are much, much more difficult. So we had 47 subjects. We had more, but 47 after we eliminated a few. And we used 64 electrodes, wet electrodes. And I'll get to the machine learning in a moment. But here are the results. And I'll explain to you what you see here. So we extracted EEG from all 64 electrodes. And then we extracted some features. After cleaning the data, we extracted the features like the power in certain frequency bands, but also connectivity and others. We found that the power band features were the most informative and were enough. We fed those features into an algorithm. So from each question, the question had variable time. So some of them took few seconds, some of them minutes. But in this simple setting, we just took the whole G from the time that the subject worked on the question. We fed it into an algorithm, those features, and the algorithm had to predict the question. This test had 36 questions that were increasing in terms of the difficulty level, from 1 to 36. 36 is really hard. And what you see on the x-axis is the predicted cognitive load from the EEG during the question. And this is the true label. And you see that there's a nice correlation, which means that we can indeed predict from the EEG a continuous measure, almost continuous test of the cognitive workload of the subject. But in this context, it's cognitive workload that reflects the difficulty of the question. So what do we do with that? Now, essentially, the output of the algorithm is like a biomarker. It's a measure that tells us the difficulty of the question. We could use it in the context of e-learning, for example, in computer software, so that when a student is learning, the computer will adapt the questions to the level of the student. If it's too hard, it would make it easier. If it's too easy, it would make it a bit harder, so it won't be boring. But here are some questions and things that you can do after you collect the data. So one question is, how many electrodes do I really need for that? Do I really need 64 electrodes, which is not very practical for neurotechnologies, right? So there are several ways to estimate it. I'll show you one way. In the questions, I'll be able to discuss other way. But for example, one way is to take sets of 10 electrodes and get the prediction, get the performance level for each subset of 10 electrodes. Then for each electrode, we take all the subsets that it participated in and give it the average number, the average performance. So we can rank the electrodes in such a way. There are other ways to rank the electrodes. And then, for example, we can take all 64, but here you see in this graph, we start from 30. So we take the 30 best channels, and then we just go one by one all the way. And you can see that even up to 10 channels, 10 best channels, there's not much change in the performance. The performance is measured with the R-squared, yes, the correlation between the predicted and the real one. But you see that then there's a cutoff, and it starts to really fall, although not that dramatically to 0.6. So then that depends on you. If you develop a neurotechnology, you want to decide the trade-off between design and accuracy. So that's one question. Another question is, what were the important features? So from the machine learning, this is not in the paper already, but we use a more sophisticated system of machine learning algorithms later on with more algorithms, and we can also rank the importance of the features using this SHAP method, which I will not get into. But here you can see the feature as beta band on FZ, delta band on POZ, and so on and so forth. There's the ranking, and you can see how much they contribute to the performance. And we'll not show that, but we can even go into more details and see how they affect the decision of the machine learning algorithms, namely, if alpha on P8 goes up or down, does it mean that the cognitive workload increases or not? What we find is that it's consistent with the literature in general. We find that indeed parietal alpha goes down as cognitive workload goes up, and frontal theta goes up, but there are different things on different electrodes, so the picture is kind of complex. It's not just trivial, just what you would find in the literature, which is not trivial, but the picture that we find from this feature analysis is even more complicated. And again, we had 64 channels times 5 frequency bands, so it's more than 300 features. And you can also rank or go down, rank the features, and then just take all of them and then the most important features. And again, you see that with 50 features, you can even get better results, maybe because you avoid overfitting for the algorithm. If the inputs are of low dimensions, then it's better for the algorithm in terms of generalization. But then you see this cut off here. Okay. So now I want to move on and show you how we try to move on with more ecological conditions and things that are more similar to video games and decision making and things that you have to do on short time scales. So here our approach was to first do some kind of conventional lab test to calibrate a measure for each individual. In the previous experiment that I showed you with the intelligence test, it was kind of a measure for everyone. We had to set the algorithm using the data from all the subjects because each one had only one question from each level. But here we are going to adapt the workload scale to each individual. And then the next stage would be to let the subject, for example, train in a driving simulator or flight simulator or something that requires some skill acquisition and then see if indeed the workload goes down. So for the calibration, we are currently using the NBAC task. It's a working memory task. It's a well-known task. For example, if it's a sequence of digits, then one has to remember the digits. It depends on the n. If n is 1, it means that if the current digit is exactly like the previous one, then you need to press something. In our experiment, you have to press either yes or no. But we also had we had several versions of this one-back task. For example, there could be here, for example, one of those 9 squares could be colored, and you just need to remember which one. But then there could be the dual task. So then you need to remember 2 things, like where it was and what was the color. And if either of them is in the next one, then you have to press. Now, n could be also 2 and 3. Then it's really complicated because you have to remember location and color, and you have to remember 3 steps back to know. And could be some amorphic shapes. So you have to, which shape, what color, and we also had the triple NBAC version. So the subjects, they do all of them. And then the definition of the workload, we have an instantaneous definition. The present one, and could be other definition, is the reaction time on that specific trial. So higher reaction time reflects a higher workload, and it's divided by the performance in this block. So only at the end of the block we know the performance, like the percent correct on the block. And again, if the block was easy, then the performance would be high. So it means that the workload is low. We divide by this. Okay, that's the reasoning. Then we use this machine learning algorithm to take periods of 1 second of EEG, extract features, and predict the workload. So we train it to predict the workload to get this biomarker for workload in that context. So here we use the other system, this wireless variable sensing system with dry electrodes. It's a dry sensor interface with 24. And here are some results. So again, we had many blocks in this experiment with different levels of difficulty. What we see here on the x-axis is the target, this is the computed workload, the reaction time divided by the percent correct. And this is the predicted workload. And we take, here in this context, we take data from all the blocks, 80% of the data from all the blocks. We train the classifier, and then we tested on 20% of the data. The held out test that it did not see, the algorithm did not see. So this is what we get when we use all the data and we check it on all the data in a sense. We use all the blocks. But the animation did not work correctly. But here we did something else. We took one of the tasks, one of the versions of the task, and we left it out for all the values of n. N was equals 1, 2, 3. And then we trained the classifier on all other tasks, and we wanted to predict whether it would predict the performance, to see if it would predict the performance on this task. And it does work well, very nice. And here it's also interesting that here it seems that the workload was high, but the predicted workload was relatively low. Why did that happen? Apparently, when we looked at the data, it turned out that the subject actually missed. He had an error, and then he kind of lost the track of the n-back sequence. So he did not have a workload because he was not really memorizing this. And then he got back to track, and the workload increased again. So we can actually calibrate an individual scale. Next step, of course, would be to see what happens in this more ecological task, like a flight simulator, and if this workload scale actually goes down. And if we can predict, for example, the number of errors. For high workload means that there's a risk for doing errors in a certain time window. So there should be a correlation between the workload that's reflected in the EG and the errors of the subject. Okay. So that's a good time point to close the first part of the talk. And I want to kind of give you some tips for research and development on EEG biomarkers. So first, as you could also see in the previous talk, signal quality is very important. So don't collect data and only then find out that you invested a lot of time and effort and the data is of poor quality. Use a large representative database with high signal quality. It's very important, as many subjects as you can, and collect the data in a way that it would have high signal quality. Then there are three major stages of analysis: pre-processing, feature extraction, machine learning. So each one of them is important, and we would like to see the contribution of each one of them. So for example, the pre-processing. What's the effect of pre-processing? What would be the performance of the algorithm with pre-processing compared to without pre-processing? So you can even remove the bandpass filter and notch filter. But more importantly, for example, ICA, if you use independent component analysis to remove some components, how would it affect the performance? Is it 10%, 20% in terms of accuracy, or just 2%? Also, it depends on the context. The effect of the number of electrodes that we've already seen. How does the performance depend on the number of electrodes? Can you find the optimal subset of sensors for the task? This is very important if you want to develop a neurotechnology which is practical and people would actually use it. Another thing is this issue of interpretability, which is a very hot subject in machine learning these days. So this is not to talk about machine learning, but there's a lot into it. I highly recommend you to learn about interpretability. So you can ask, what are the most informative features? For example, if we use advanced nonlinear measures that I will show you in this next part of the talk, do these nonlinear measures actually contribute beyond the conventional measures like the frequency bands? And how does each measure affect the output? That's really interesting. And you can even go into what's called local interpretability and look at particular decisions of the algorithm. For example, if the algorithm was very confident and made the correct answer, what drove this answer? If the algorithm was very confident but was wrong, what happened there? So we can actually reverse engineering these machine learning algorithms to some extent and understand how they work and then get some basic science from that, which is really interesting. And again, those machine learning algorithms, they have hyperparameters, those general parameters that set the algorithm. In a neural network, for example, the number of layers, the number of neurons in a layer, architecture, but there could be decision trees, support vector machines, other algorithms. So you have to tune those hyperparameters and also ask what are the best performing algorithms. So these are typical questions that one would ask, and I recommend you to use these kind of tips if you set out to explore and look for biomarkers. So now I'm switching gears. Hope you're alive at this time point. Unfortunately, there's no feedback. I would rather prefer an informal talk and see the audience and have questions in real time, but we'll get the questions at the end. So now I'll talk about critical brain dynamics. And I'll start by some motivations. There are different psychiatric and neurological disorders like epilepsy and schizophrenia that are associated with imbalance of excitation and inhibition. More correctly, impaired balance of excitation and inhibition. Two major systems in the brain that, excitatory neurons, inhibitory neurons that the balance between them is very important for activity. So we also see that in disorders of consciousness, mild cognitive impairment, and Alzheimer's. Of course, in each disorder, it's a different pattern, but they're all related to some extent to this impaired balance of excitation and inhibition. And as you will see, this framework of critical brain dynamics is kind of natural to deal with that because it deals with critical phenomena, with working on the border between two qualitatively different types of behavior. So now I'm switching to some concepts from physics, actually, phase transitions and critical phenomena. So we all know about phase transition. We know that water can turn into ice, ice can turn into water if you heat it up. So there's a certain critical temperature at which there is this transition between water and ice. And similarly, if you take a piece of iron and you cool it down, it becomes a magnet. But if you heat it up above a certain temperature, it stops being a magnet. So there's a transition of phases. Physics studied those phase transitions and found that there are some general principles that govern those phase transitions. For example, near a phase transition, the system displays what we call scale-free dynamics. So there are certain power law relations. There is no characteristic scale. So there's fractal behavior. Power law means that the function behaves, P of S is like S to the power of alpha. Here, alpha is negative. And if we plot it in a log-log scale, we see just a line with a negative slope. So that's the hallmark of power law behavior. This is what we see in critical systems. Another thing is universality. If you look at these alpha, if you plot the corresponding power laws, and I'll be more concrete in a moment, you can calculate this exponent alpha, namely the slope of this line, and you find that very, very different systems show the same critical exponents, the same values of alpha or other exponents, which means that they do not depend on the microscopic details. So for us, as brain scientists, if the criticality theory is relevant to the brain, it's nice. It means that we can say things without having to know the details of the ionic channels, the transmitters, and things like that at the neurobiological level. So in recent years, I would say since early 2000s, there's been work, experimental and theoretical, indicating that the brain, or more precisely the cortex, is near critical. It's not exactly critical, slightly subcritical, slightly below what we call the critical point, but very, very close to the critical point. That's the idea. What does it mean? It means that we think, that's the hypothesis, that the brain operates on the border between, in this case, premature termination of activity propagation and exponential blow-up. So let me illustrate that. It's kind of heavy. Maybe some of you did not expect this kind of theoretical ideas in the afternoon. But let's just imagine that there's an axis here. And rather than temperature, here we have the neural gain. So an excitation-dominated system would have high neural gain, and an inhibition-dominated system would have a low neural gain. So if the gain is lower than 1, it means that when a neuron is active or a group of neurons is active, it activates smaller group in the next time step, and then smaller and activity decays. On the other extreme, if we have too much gain, too much excitation, then the system would blow up like a nuclear chain reaction, like an atomic bomb. But somewhere in between, we have this critical dynamics, and we have cascades of activity that can be preserved for a long time. Now, because the system is stochastic, namely it's not deterministic, we don't know what's going to happen at the next time step, sometimes those cascades will be short, sometimes they will be longer, but they can be longer. And there's a lot of theory on these kind of systems, and some very general theoretical conclusions about systems at the critical point. And the theory predicts that in critical systems, namely when this sigma parameter, the branching parameter or the gain parameter, these are alternative names, when the gain parameter is close to 1, if we look at those cascades of activity, we will see that they have a power law distribution. with an exponent of -3/2. And we call them avalanches, neuronal avalanches in the context of neural activity. So let's see. So here's a simulation. There are neurons here in this simulation. Each one is connected to neighboring simulations. It's a simulation from a friend of mine, Viola Prisman from Germany. And each time there's a cascade, and you can see the avalanche size here. Now, if you collect a lot of avalanches and you would plot them, you would see that it gives this kind of distribution. This is the size on the x-axis, the probability for a given size, and it's a parallel until some cutoff, which is related to the number of neurons in the system. And the exponent, or the slope, is really close to -1.5. What happens in real data? So these are results from cortical cultures. So it's a piece of cortex that is grown in a dish on an electrode array of 64 electrodes. And this was done by Dietmar Plantz and John Bex in 2003. They were able to show that you get this nice parallel, again, straight line in log-log coordinates of avalanche sizes. I didn't tell you yet how you find those avalanches. I'll try to explain in a moment. And these are some results that I obtained when I analyzed MEG, magnetoencephalography data, in 2013. And so again, these are avalanche sizes and the probability on the y-axis, and we see a nice straight line until some cutoff with an exponent close to -1.5. So how do we do the avalanche analysis? My experience shows that it's hard to explain that first time when you listen to it, it's hard. So I'll explain it briefly, but don't really try to get all the details. I mean, just the idea is what's important. So what's important to know is that we discretize the signal, and then we cluster them into some spatio-temporal cascades. So in contrast to what you usually do with EG, here we discretize. We take some thresholds. Here it's in unit of standard deviation of the signal in each channel, and then we identify those peak events that are beyond the threshold. If we do that, we get a raster plot like that. So in this case, this is MEG data, so you see many channels on the vertical axis, and the x-axis is time. So 10 seconds. And you can see that there are some vertical stripes of activity that are related to the correlations between sensors, but also to propagation of activity. So we'll not get into all the details, but some of them really extends to hundreds of milliseconds. And this is an illustration. What we do is we take some parameter, which is a time scale, a certain beam, and we beam the data into time beams. And then we look for quiet time beams. There were no event on the array that crossed the threshold. And this would be an avalanche, something in between silent beams. As you can see, the result also depends on the width of the beam. So if I take a higher width, like a higher time scale, then what we would get is a concatenation of these three avalanches into one avalanche. So there are two important parameters, the threshold, which is not that critical for the analysis, and the time being, which is important for the results. So that's why I needed to introduce this. Now, we also extract this, or estimate the neural gain parameter. The way we do that is we take those avalanches, and then we take the first two bins of an avalanche. So we had some quiet period in the data, then we had some events on the array, on some electrodes, and we are looking at how much they were amplified in the next time beat. So in this case, it's just dividing 2 by 2. It could be 3 by 2, 4 by 1, whatever, 1 by 4. We just take all the avalanches, we collect this amplification ratio, and we average over a certain period, and we get this estimate of the gain parameter. I think I'm okay with time. And here's an interesting plot. What do we see here? We repeat the analysis for different time scales. This is EEG data. So it's 500 Hertz, so we can do time beams of 2 milliseconds, 4, 6, 8. And for each time scale of the analysis, we calculate the branching parameter. This is an average across many subjects. It's just resting state data. And this is the exponent of the parallel. We fit a parallel, we find the exponent. And what you see is that there's a curve, but there's a certain point that when the branching parameter is close to 1, the amplification is close to 1, the exponent is indeed -1.5, as theory predicts. This is from MEG data. So we just look at several time scales and we see that. And later on, we also realized that the whole curve is informative. And we actually look at the whole curve and we extract some parameters from that. And we call it multi-scale criticality because we just look at the curve and we fit it with a line, and we calculate the slope and the intercept. And so we get many parameters from this analysis because we have things beyond the alpha and sigma. I mean, I'm not getting into all the details, but we call them multi-scale criticality parameters. They characterize the properties of the system in terms of how far it is from the critical point. And now we're going to the interesting stuff. So the analysis, maybe you missed some of the details. It's fine. It's kind of complex to hear it first time. But suppose you do this analysis. This is in cortical cultures. It was a very interesting result. So the black line is the curve when the dish is normal. The solution in the dish is normal and the cortex is healthy. Now, what happens if you block the excitation, blocking this NMDA and AMPA receptors of excitation? Then you get this blue curve, which we call subcritical dynamics. It falls very steeply. We cannot see the large avalanches. If we block the inhibition, we get this kind of behavior. It falls here, but then if there was a large enough avalanche, we don't see the intermediate range here. In this example, we only see those large avalanches that are across the whole system. So this is like an epileptic-like behavior in the system. So the avalanche analysis is very sensitive to this balance of excitation and inhibition. I need to speed up because I want to finish in a few minutes. So the idea is that we can associate deviations from criticality with brain disorders. Subcritical dynamics is related to premature termination of activity propagation and perhaps to disorders of consciousness, whereas supercritical dynamics is related to exponential growth of activity, high synchrony, and more to epilepsy or hallucinations, which are also some kind of uncontrolled brain activity. So here are some interesting results. These are data of sleep deprivation, 36 hours sleep deprivation from healthy subjects. And here you see the time awake until recovered sleep. And this is the gain metric, this sigma parameter. You can see that it goes up. And we know that people that are sleep deprived can experience epileptic seizures. So it kind of makes sense that the brain becomes more excitation dominated. And also there's a certain circadian envelope. And after recovery sleep, it goes back down. If we plot this gain metric here on the x-axis, and then we plot a behavioral measure of reaction time, we see that they are correlated. So during the experiment, the reaction time goes up as subjects are more and more sleep deprived in correlation with this gain metric. So it's also related to behavior. It is correlated. Now in the context of epilepsy. So what you see here, each point is a subject, and this is just analysis of resting state activity, and we get the sigma measure, the alpha measure, which is the slope, the exponent, and kappa is another measure I will not describe, all related. And here you see the epileptic patients, and you can see that these are MEG data, and you can see that the patients have higher values, which means that the brain is closer to the critical point, or I wouldn't say beyond that because that would mean already seizure, but this is only resting state activity, not during the seizure, but it's already reflected. I think I'll skip that one, but the take-home message of this slide is that if we look very close to the interictal spikes, if someone knows about epilepsy, these are small periods that the subject doesn't really feel them. It's not seizure. But if you look at the avalanches very close to them, we find that we can see this bump in the activity. We see that there is no scale-free behavior anymore. The system is supercritical, and it's very similar to what we could see in the dish. So activity in those spikes show this, it's kind of, the brain is not balanced. Too much excitation compared to inhibition. Again, if we compare the periods which are 1 hour before a seizure, this is from another data set, EG. If we take periods which are 1 hour before a seizure compared to interictal periods, which are at least 4 hours away from seizure, we can see again difference in some of our measures of multi-scale criticality. There are many of them, so I'm not saying which exactly, but the idea is that using those measures, we can see differences, for example, in the context of schizophrenia, from another database, in mild cognitive impairment, which is a precursor of Alzheimer's disease. and also in the disorders of consciousness. So for example, the gain metric, if we look at vegetative state, minimally conscious, emerging from minimally conscious, it's very low compared to control subjects, which means that their brain is indeed subcritical, kind of disconnected. But if we look at some of the more detailed multi-scale criticality metric that require us to plot some functions as a function of the time scale of the analysis, then we get more refined measures that can actually show differences between the different subclasses. So this is also related to things that were mentioned in the first talk today with the FNIRS data that could also be helpful for disorders of consciousness. Finally, I'm close to the end. We can also do neurofeedback. So we're going back to BCI. And we did some experiments where we're actually trying to modulate this branching parameter, the sigma. So we use the 64 electrodes, the high amp, and we extract in real time, estimate in a few seconds of the sigma, just calculate avalanches and calculate the sigma, and then we feed it back to subjects. We actually use some TED Talk and we modulate the sound during the talk. And subjects actually learn to regulate. So we so far just tried to down-regulate because we did not want to get anyone to maybe experience epileptic seizures, but we are going to try that very cautiously also to upregulate this sigma parameter at some point. And I will not get into the details, it's a whole talk, but the preliminary results we have so far that subjects can indeed down-regulate the neural gain parameter from the 64 electrodes. And that there are behavioral consequences because it's a long experiment and we are doing also cognitive experiments. And we can see that the behavioral consequences are consistent with what you would expect from a deviation towards subcritical dynamics. I will not get into details at this time. And finally, my last slide, I think, is almost is just to show there is a connection between the two parts of the talk. This is a paper that was published online on the bioRxiv on May 26th, not long ago. And they talk about scale invariance in brain activity predicts practice effects in cognitive performance. So the basic idea, it's an fMRI study. They know that there are individual differences in reaping the benefits from practice. And basically their claim is that if you look at the bold signal of the fMRI and you do a certain criticality analysis, it's analysis of what's called long-range temporal correlations, you can see that subjects that were closer to scale-free behavior benefited more from practice. They showed better skill acquisition. So it could be interesting to see if that works also with EG data. But here's a relation between skill acquisition and criticality. So to summarize, there you have my email. If some of you have questions and want to send me emails, I guess I will not get 1,300 emails, but I will be able to answer some. So I showed you that MEG and EG data in human subjects show the signature of neuronal avalanches and supports the hypothesis of criticality. And I hope I convinced the criticality-based metrics that are kind of driven from some theoretical ideas about how the brain works could provide some useful neuromarkers for a wide range of disorders, in particular those associated with altered excitation inhibition balance, like epilepsy, schizophrenia, autism, others. And to wrap up, I think that if you approach a certain project where you're interested in biomarkers, try to use both spectral features, which are common, very useful, but also complex nonlinear features like measures of criticality and connectivity and others. And then use machine learning algorithms and let them decide what's important. So don't subscribe to any religion. I'm an oscillations person, I'm a criticality person. Just do the job systematically and let the machine learning rank them and tell you if those complex features are important or not. So before I thank you, I just want to tell you a little bit about something that we have here in Israel, which I think is really cool and might inspire some of you out there around the world. So we have this brain tech or neurotech community. We call it Brainstorm IL. This is the website, brainstormilisrael.com. And this is how the website looks like if you land on it. And it's in English, or mostly in English. Some of it is in Hebrew. And this was only established like a year and a half ago here at Ben Gurion University, but it grew up to a national community with over 1,300 members, which organized already more than 30 events and has partners in the government, in the industry. And basically, now it kind of combines people from all universities in Israel, essentially. And each local community, in each city or university, they have monthly talks by brain tech entrepreneurs and people who represent needs, for example. We have workshops, community days, local collaborations, and we're even establishing neurotech hubs, just spaces in the university where people could work on their projects. And there are national activities, like recently we had this NeuroPitch program where groups of students came up with some ideas for brain tech products. They worked on that with mentors. They didn't do any empirical proof of concept, but they just kind of crystallized the idea and gave a pitch on that, and there was a competition with a prize, which was really cool. We are establishing a course, a BCI for ALS course, which we plan to end with a cybathlon, and more and more. Neurotech magazine, already we have, today, the second issue went up online, hackathons and more. So this is really cool, and these are some pictures from a hackathon we had last year in our university, and I really recommend to take a look at that and maybe establish neurotech communities at your local countries. So thank you very much for listening. I know it's been probably heavy for many of you, high cognitive workload, so to speak. I need to give credit to many people from my lab, Amjad, Tomer, Oshrit, Nir, Miriam, Eyal, Nir, Lahav, Fuchs, Shai, all of them contributed to the amazing things that were done. It wouldn't have been done without those amazing guys. And thanks to the funding agency. So that's it. Questions?
Thank you very much, Oren. This was really interesting. So we have many questions. You can also click on the Q&A button if you want to see them. So the first one is from Joao. Is it possible that in the adaptable versus non-adaptable decoder, the subject got worse because they did not feel the sense of agency?
Yes, in the beginning of the talk. To some extent, yes. Yeah, we know that one of the subjects in the experimental group, in the beginning, he didn't believe that BCI is actually real. He thought we were tricking him. So he had kind of low performance. And then at some point, this was the guy that kind of improved later on. He realized that it actually works. And then he got really better once he felt that he was controlling the video game. And conversely, the guys in the control group, maybe they lost interest. I hope it answers. I don't know.
Ridika is asking what age group you took, and is there any gender variability?
It depends on which of the projects that I described. So for the first one, the BCI, these were just students in the university, so in the 20s. Also for the intelligence test that we did. So of course it's different when it comes to the patients, but the kind of the conventional studies that we did were mostly university students in their 20s, I guess, but the age group is important. So for example, in the intelligence test, it's the same intelligence test, but it can be used to calculate the IQ, but the IQ would depend on other factors like the age. So it's important to take this into account in the analysis, in the behavioral analysis. So for example, we just try to predict the question. Maybe if we would predict the IQ level and normalize by the age, we would do better in some sense. Yeah.
And Anna is saying there has been a lot of discussion on epilepsy in this webinar, but this is the first time schizophrenia was discussed. Have you worked on that? Is there a reason it is in general less discussed in biomedical studies than epilepsy?
Yes, it's a great question. So it falls back to the issue of what's the difference between neurological and neuropsychiatric disorders. So neurological disorders are where we know we have kind of physical evidence to a change. Like it could be a lesion, but in epilepsy, we see it in the brain activity. We see it very clearly in EEG. So long time ago, those patients with epilepsy, they were thought to be mental health patients. I mean, like crazy people. But now we know that it's neurological disorders. On the other hand, in schizophrenia, although there's been much work at all levels, there is no clear biomarker that tells that someone is schizophrenic. It's only behavioral, and we are looking for that. And that's why we need more data, more EEG and MEG data, for example, or other modalities from schizophrenic patients. And for me, it's very important to have longitudinal data. So follow the same patients a long time and see if some of those brain dynamics measures change, if the subject gets better or worse, and what does it mean? So schizophrenia is way back in terms of our ability to diagnose and tell something objective from EEG, in contrast to epilepsy. So epilepsy is like the low-hanging fruits currently.
So Sana is asking, have the achieved biomarkers been used for rehabilitation monitoring?
I don't know. I think it's a good question for you, Christoph. But you have longitudinal data from rehabilitation. Do you use some kind of markers that are EEG-based?
We have a couple of biomarkers like collateralization index and event-related desynchronization biomarkers, and they fit very well to Vogelmeier improvement when we do BCI rehabilitation. Then Ridika is asking which connectivity measure is best for neuromarkers.
So I don't know, I did not discuss connectivity here, but essentially there are many ways to do analysis of connectivity. One first calculates this connectivity matrix. So for example, you can take the correlation coefficient between a pair of channels, do it for all pairs of channels. That would give some kind of a continuous matrix. Then typically people binarize it if the correlation was above or below a certain threshold. And then there are many graph theoretical measures like small worldness. So you do the path length clustering, the ratio, which is the small worldness, and other measures of graph theory that could be all informative. So yesterday I saw a paper in the context of detection of epileptic seizures, where they use some connectivity measures to identify the onset of a seizure.
And Cheng is asking, is a time pin with only one peak considered an avalanche?
Yes. That's a good question again, because intuitively one would think that avalanche could be a large event, but an avalanche is anything between a single event and more events. So we detect those peaks, and could be an avalanche of a silent beam, one event or two events, and then another silent beam. And actually those are the most common avalanches that we see in the data.
And an additional question, why positive and negative peaks are considered?
Yes, it's a good question. So in the analysis that I showed, I consider both positive and negative. So for example, in the MEG, both of them are important, and also in the EEG, but I did the analysis only with positive peaks, only with negative peaks. The results are relatively the same. So it appears in a book chapter that you can find on my publication list, in a book about critical brain dynamics. There we did this analysis, which looks at positive and negative separately. So we know that from ERPs that there's an importance for negative and positive peaks, but in resting state signals, I think it's better to consider both of them. In local field potentials, people actually look at the negative local field potentials. They are considered to be the more informative.
Ramakrishnan is asking, can you mention the name of cognitive workload assessment test, which you mentioned at the beginning?
Cognitive workload assessment test? Raven. It's not, yeah.
Can you maybe type it into the chat so that the listeners see how it's written?
Now I kind of lost track. I think, now it's above.
Just in the chat. There's a chat window where you can post it to everybody.
For some reason I don't see. I see that now. So it's Raven test, and it's named after the guy who invented that, Raven.
So this was very nice, Oren. Thank you very much. It would be nice if you could answer the two open questions just by typing in the answer.
Okay, this by Polamikau. Okay,
yeah,
I will
And so this was really nice. It was a pleasure to see you again. And hopefully I see you at Neuroscience in Washington.
I wish I could come. Thank you very much.
Thank you. Bye. And in the meantime, I can already see that Adriana is online, so I unmute her. And I already see you. Please enable your microphone. Good morning. Hello.
Can you hear me?
Yes, I hear you and I see you.
Well,
Nice to have you.
Thank you, same. Nice to be
Where are
here.
you at the moment? In Georgia?
I am in Atlanta.
Okay, very nice. So please click on the share screen button. So Adrienne Randolph is an expert for many, many years and doing a lot of BCI projects for many, many years. And I'm looking forward to her presentation today in the summer school. Please go ahead.
Thank you so much. Good morning, good afternoon, good evening to you all. I'm excited to be here. Thank you so much, Christoph, for the invitation and being able to join everyone this morning. And I am going to discuss perhaps the different way we're using brain-computer interfaces at the Kennesaw State University Brain Lab. And as you may have just heard, we are located just north of Atlanta, Georgia in the United States. So Kennesaw State University is the third largest university in the state of Georgia at 34,000 students. And we are excited that we are doing this sort of work in partnership with others around the nation and the world. And so today, just talking about brain-computer interfaces as a new direction in human-computer interaction. First, I'll give you a little bit of background about the Brain Lab and how we came to be, and then talk about a related field, neuroinformation systems, some tools within brain-computer interfacing that we're using in applications. And that's really the crux of the talk here, some examples of human-computer interaction and real-world uses for brain-computer interfaces. First, the origins of the Brain Lab. And I share this picture here where you may notice the founder and host also right next to me in the front row here at the second International BCI meeting. So if you'll look at the front row, and there's a familiar face, Christoph, right to my, I guess to my left in the photo. But you'll also notice that in 2002, there were only 90 attendees, and this conference has grown quite a bit, including looking at the summer school where over 1,000 registrants really says quite a bit about the field. I first worked under Melody Moore Jackson, who was part of one of the first implant teams with Phil Kennedy for brain-computer interfacing. And she established the Brain Lab at Georgia State University, also in Atlanta, Georgia, in the US, and has since established the Brain Lab over at Georgia Tech. Well, as classically described, brain-computer interfacing for helping people who are living locked into their bodies due to ALS, severe stroke, cerebral palsy, and of course, meaning that the person is severely paralyzed and unable to speak, but we presume still cognitively intact. So we're excited brain-computer interfaces does offer an opportunity to connect these individuals to the real world in a proactive manner. In 2007, I established the Brain Lab at Kennesaw State University, and I'm using a number of different neurophysiological tools, EEG being the primary in a non-invasive way. So I make a joke that even though the Brain Lab has now grown and moved to a larger space at the fringe of our campus, it's not because I'm drilling open heads, quite unfortunately. In addition, though, to EEG on surface electrodes, I'm using eye tracking, galvanic skin response or skin conductance response, electrodermal activity, whichever term you prefer to use, as well as detection of emotion from facial muscles and minute changes. And lastly, from functional near infrared, so blood flow in the brain. How does this relate elsewhere? Well, my PhD is in computer information systems. And so that guides my direction in looking more at the design and application of brain-computer interfacing. So a related field that has been established is neuroinformation systems, or NeuroIS. And the idea of NeuroIS is that we can use neurophysiological tools and neuroscience principles to understand more about people and their interactions with information technology, or IT. And that our traditional means, our observation, survey, those are just scratching the surface and looking at behavior. And that we need to look in using these more, a triangulated, robust mechanism to understand the individual. Further, we see how brain-computer interfaces fits into this by appreciating that it's not just using tools to understand, but also using these neuroscience tools as being incorporated within our information technology artifact. With neuroinformation systems, we do have an annual conference, which I invite you to join, and it takes place in June, the first week usually of June, and it is in Vienna, Austria. So same time if you are logging in as alongside Christoph. Next year, we hope to be back in Vienna. Of course, this year it was virtual.
Sounds good.
You'll also notice another face there in the bottom corner, which Gernot Müller-Putz, downline from Scheller, who is on our founding board for Neuroinformation Systems and an active member. So again, welcoming you all to check us out. So what are some of the brain-computer interface tools? Well, in a basic setup in the Brain Lab, you can see here just the bioamplifier, 1020 electrode cap, software to do processing. And of course, that takes many different forms and different software, different hardware being utilized. I like to classify inputs and outputs, or inputs a little bit differently, where I describe directly being that EEG from surface electrodes. And so we look at mu, rhythm, P300 as input for control. In understanding individuals, we examine particular frequency bands. So understanding their frontal asymmetry with alpha, or measuring cognitive load using an engagement index. There's other ways, which I'll say are more indirect, where it is a function of your thoughts. And so we have changes in our brain blood flow, or how much sweat we're generating according to those internal expressions. So how can we use these things? Well, first, we break it into active and passive brain-computer interfaces, where active is appreciating that we're trying to control something, versus passive being that we're looking to incorporate into a feedback system. So not actively controlling anything. Some have used it to control video games, driverless cars, prosthetics, and this being the one that President Obama shook this hand, or virtual reality, for example. In the KSU Brain Lab, the Kennesaw State University Brain Lab, we're using brain-computer interfacing for both active and passive ways. Non-traditional assistive technology is how I categorize a brain-computer interface, where we are, again, helping individuals communicate and control their environment. And that's in partnership with individuals from Georgia Tech, as well as the Wadsworth National Center for Adaptive Neurotechnologies. And so you'll know that group as Jonathan Wolpaw, Teresa Vaughn, and company. We're using neural input to control devices, things like Google Glass, and I'll describe that a little bit later in this presentation as an example. And certainly ongoing ways that we can help locked-in patients better communicate and proactively control their environment. We're also exploring brain-computer interfaces for improving our abilities. And one being, can it improve our physical ability? We've certainly seen examples in the literature around neurorehabilitation applications. So I'll give you a quick example of how we use a basic video game interface to test someone's ability for improvement. It's also been used in the lab to understand someone's mental state. So in this case, a student training with a brain training game and measuring their EEG to in fact, see changes in their attentional focus, things that others were able to observe as well. And interestingly, seeing an equivalent to a pharmaceutical treatment for ADHD. The last being our work in cognitive load and having a real-time measure for cognitive load in partnership with a group in Montreal at the Tech 12 Lab, and also appreciating cognitive load as it changes real time for student learners. So first, let's talk about communication and control, again, in a classic sense of the use for brain-computer interfacing. Well, we've seen that we can use motor imagery and understand thinking about opening and closing your hands versus being at rest can move a cursor. So in this case, we see my then provost of the university, Ken Harmon, just on a first try at moving the cursor on the screen, where the ball is moving at a steady rate across the screen, and he's controlling the Y position according to mental imagery. So he's very still because he's not actually using his hands. He's using the thoughts of opening and closing his hands. Well, we take that paradigm and try to see if training over a certain amount of time will in fact improve someone's physical abilities. And so we had individuals come to the lab and train over 5 sessions with a mu-based brain-computer interface. And mu being that physical center where you're thinking of your hands moving for the brain. And we had them play a round of Wii tennis, because much easier than going out on the court to measure their ability or hooking them up to some sophisticated sensors. Instead, we tested it through a video game interface. And so they played Wii, then trained over 5 sessions for the week, and then played Wii tennis again. And we did get an incremental improvement in their scores, indicating that practically so that they are improving due to training with brain-computer interface, as they were not engaging in anything different during that training period. The other paradigm that we actively use is P300, so that oddball response. As you may have heard, if something is being presented at a randomized fashion and the item that you want appears on the screen, is flashed, then you will have a response that we're able to pick up. And so we can distinguish that desired response from the other responses. And so you see on the screen here, my student Josh and his EEG streaming, this being collected through BCI 2000, the open source platform that's offered by Wadsworth. And he almost gets his name exactly right, spelling his name using P300, and this being an untrained system. So we did not specifically go in and classify his signal ahead of time, but use a general parameter. And so for an able-bodied person, this is often enough. You also see that we are using the g-tec bioamplifier. Now, again, to just refresh your memory, and we see more sophisticated systems where there will be faces, but if we're trying to complete BCI, you focus on the eye. When the row or column is highlighted, your brain is having a response. So we use that paradigm also out in the field, and going out to work with patients who are living locked in or nearly locked in this case, someone due to cerebral palsy. Actually, this one due to a diagnosis of ALS. And you may see a face that you recognize as well, Teresa Vaughn in the bottom corner, and a member of the Brain Lab here, Steve Krantz, our Director of Innovation, as we use the P300 paradigm to see if we can, one, classify this person's signal, brain signal, in a way that we get a reliable categorization of their response to then be able to tell us proactively what they want to spell. We've used this P300 paradigm to also look at real applications for today. So many still are using Facebook, and we thought we would too. So we used the P300 as an underlying application mechanism to allow someone to communicate using P300 as input to Facebook, since there is an overlay that you can program it to. So the BCI Pi 2000, so Python-based version of BCI 2000, was used to code this application and linked with then an 8-channel EEG bioamplifier. So you can see that there is both an iconic version and a character-based version. So the iconic being able to select some of the most common choices within Facebook for making posts or interacting. And then to refine your interaction, being able to spell using the, again, classic matrix. Well, we also use P300 as input to Google Glass. You may remember that in 2013 that Google output this head-mounted display unit where it was like seeing your computer screen about 8 feet in front of you, and that this device could do everything that your smartphone could do. Well, because it's a little computer, but on your face. And that's where we thought we could capitalize on that idea by being able to not control Google Glass through its classic means, which is by tapping or by voice commands, but for someone who is living locked in, use their neural input. And so we built this using BCI 2000, again, input from a g-tec amplifier, as you can see in the bottom here. And it's a proof of concept. It works, but as you see, there's multiple components there. And ultimately, we have the bioamplifier that's collecting and recording the signal. We're running this algorithm on Java-based input, but also using the open source platform that comes with the Android operating system for Google Glass. So when the icons would flash, we'd be able to focus on the particular choice. And again, as with the P300 paradigm, be able to select that. And so then we can tie that to the common commands within Google Glass. Well, we were excited about using this because when you go to visit a patient, there's limited real estate, meaning that there is a lot going on in their environment just to keep them alive. So when we come in the field for home use with the brain-computer interface, we are literally rolling a large suitcase with the laptop, the bioamplifier, our own monitor, and we're looking to disrupt that person's environment where it's already taken up, their television, their computer, whatever's been placed there for their enhanced quality of life. In this case, the computer would be on a portion that's not being utilized, and that being their face, so that we might be able to better adjust their viewing angles versus a monitor that's sitting out in front of them, and that we can use a signal that doesn't need training, this P300 signal, as input. The other end is there's a caregiver, usually. So that might be a loved one or a doctor, and usually not someone who's trained with brain-computer interfaces or even with technology in a deeper manner. Well, in this case, with the Android platform, you can see everything the person is seeing on their head-mounted display on a cell phone. And so there's shared control that can take place. Well, we're looking to continuously improve quality of life for patients in their environment. And another way that we found is through communication of their health and comfort. When we go visit, it is imperative that before we get to the neat work of putting electrodes on someone and seeing if they can control a device with their minds, that we need to see if they are okay. And so we go through a series of questions, a triage, just to make sure they're comfortable before we start, because that has great bearing on their success in using the system. And what you're seeing here is our prototype for communicating comfort and care from a scanning interface. where there are areas of the body that are scanning at a regular rate, head, mid-torso, and so on. And the items for selection are informed through past research and observation. So conversations or what the person has shown to be troublesome to them, or have been things that they want to communicate. And so we better inform the system and promote the things that they have communicated versus a larger corpus, a larger body of items that they could select from. And that helps speed up the interface for the individual. The last thing I want to share is that we are actively working in this area of cognitive load now. And this is from a National Science Foundation funded grant under the Education Directorate. And you see that we're using a full suite of neurophysiological tools here, trying to get the full body experience of a student in a simulated learning environment. So with a classroom instructor present as a student works through their exercises as they would in an actual experience. The student is wearing eye tracking glasses as well as an EEG head cap. Well, in this case, we're tackling the area of chemistry learners. And you may think back about your science experience, and hopefully you have fond memories of having taken chemistry and it going well. But for some of us, like myself, it did not. And that is because chemistry is full of abstract concepts, and you must understand one model or concept before you can go on to the next. The interesting thing is there's no set pattern for how these models are presented to students, and this is across that field. But in order to learn, you have to be able to assimilate information. And to do that, you're working with a finite space within your mind. And this is that working memory space. And it is bounded by the cognitive load that you experience. Interestingly, we suspect individual differences may influence how well you're able to moderate that cognitive load or how well you're able to learn these various concepts. So that's where we dove in. To give you a little bit more about cognitive load and cognitive load theory, well, there are three components when we talk about it in the case of learning. The first being this extraneous load. And this is the load that instructors can create. So in the manner that we present the information, perhaps overcomplicating things or hopefully simplifying them. And that's something that we want to minimize in terms of not making it too complex for an individual. The next is just the inherent load or complexity of the task itself. Are we talking about neuroscience? Are we talking about, as we classically say, rocket science? Well, that's just how the nature of the subject. So we just try to manage that. And the last is how we can supplement our learning through schema and giving ourselves tools to help better assimilate that information. And there we try to maximize. So let's take that into the case of understanding chemistry learners as they work with different models. Those models may be 3D models that they physically manipulate. They may be 2D, it could be a picture on paper, or it could be a virtual model. So something on their computer screen that they're manipulating. And we put them into this environment with an instructor giving the classroom exercise and being available as they then work through the different questions using the particular models given. And as I described before, different neurophysiological tools being used to understand to complement these observations that we're making. Well, we have been working for the past 3 years in understanding learners in this context. So we take a 16-channel, in this case, biosemi bioamplifier out to the field and Toby glasses that are placed on so that we can see the person manipulating the model. And that being different from an eye tracking bar that you may attach to a screen, since obviously not all of these cases are screen-based. We've also been utilizing an engagement index for measuring cognitive load, and this being based on the work of Alan Pope. And so we look at this ratio of frequency bands between beta, alpha, and theta. So you can see a student working with the instructor as she's manipulating this 3D model, how she is working through the exercise of mashing parts together, and this is from her perspective. All the while EEG is being recorded. Well, just an example of one exercise. You, in this case, will notice that we're looking at a negative logarithmic graph. So the higher the bar, the lower the load, if you will. And the lower the bar, the higher the cognitive load experienced. And as the student is working along, they experience higher load for these latter questions. Now, that's encouraging because we can see as the person works through, as the various students work through the points of the exercise, that we can measure how hard their minds are working, how hard their brains are working at these different points of the exercise. And then utilize that information to modify curriculum and help bring them along in a better, we call it scaffolded way. Scaffolding meaning you're providing those schema, those tools to help the student better learn without becoming overloaded. So from this exercise, when they were exploring with the model, so taking a look at the physical model or whatever model was given, in this case physical, versus answering the questions that went alongside the exercise, they had a lower measure for cognitive load working with the model than the questions. Okay? And we also tried to correlate this to various individual characteristics. So, I mean, we often talk about you're manipulating models, maybe it's your spatial rotation ability that has some influence on how well you do. And certain individuals may have better ability in these cases. So one, we need to tease out the type of spatial ability we're talking about. And we can do that through a field dependence test, which is kind of like finding the hidden figure within a busy array. And then this rotations ability is, can you turn an object and rotate it in your mind and see the other sides and what it looks like on the other side? So how well do you do that? Interestingly, those are two different things, two different abilities, but described as spatial abilities. So for this exercise, we saw a negative correlation between that ability to find the hidden figure, or in the United States, we say a Where's Waldo paradigm, versus no correlation to cognitive load for the rotations ability. So we can't just make a blanket statement about these abilities. We have to understand the true nature. And we're better able to understand this association as someone goes along in their learning journey by using EEG, and in this case, a brain-computer interface-based paradigm. Where we want to go next is built on the work from partnering with the Tech 12 Lab in Montreal, and that is using a real-time measure for cognitive load. So we have the engagement index, we have paradigms for understanding low and high cognitive load from psychology for years. So we can put someone into a forced low and high situation, measure what's happening in their brain output, and then use that back in the system to mark, are they experiencing high cognitive load or not? In the case with partnering with Montreal, we're observing then someone navigating a browser and a shopping website and making calculations, for example, and how well that design supports their easy navigation or not. Well, in this case, we would look at how does the curriculum support easy navigation for the student and understanding what they're learning. We also want to investigate, is the classic sense of the Pope Engagement Index the right way to go about measuring cognitive load? In this case, as we're looking at models. So are there other brain regions that are better utilized in this calculation? The last thing I want to discuss and leave you with is we are not all the same. And although we generally map our brains to be the same, and I do say generally, those abilities do differ. So something that we have investigated over time is our individual characteristics and how they match with various brain-computer interface technologies. So you can imagine if you have become a better athlete, or you're able to imagine your dance in your mind, that perhaps you're better at imagining that physical activity needed for mu-based control. And it is a logical connection. Well, there are other things as we consider functional near-infrared, for example, and that blood flow, the volume of oxygenated blood in a certain area. If you have better blood flow and perhaps being able to in a more refined manner control that response. Often, if you are thinking of language, for example, and you have a functional infrared emitter and detector, it's placed over the language center. And as you think of counting quickly, you have blood going to that area, the Broca's area. As you think of a nonsensical word, blah, blah, you have a decrease in blood flow. So that's something you are actively thinking and using as a paradigm to control a binary control, on or off. And as you may be older, unfortunately, that flow does decrease. So as we looked at these individual differences, skin conductance response, we found that people in their early 40s who are younger, male, lighter haired, play video games, regularly drink alcohol, and do not meditate were better at controlling their skin conductance response. And that sweatiness factor is something that has been used as input to control a brain-computer interface. For example, a person on the west coast of the US some years ago now was in a long-term round-the-clock care situation, being fully locked in, and had a nurse on site to take care. Unfortunately, it seems that nurse did not fully believe that person was in there. And the team brought a galvanic skin response or skin conductance response based system to see what they needed to say, what they needed to communicate. And it took him all day to do so using the system as the character scrolled across, generating an activation from the skin conductance response to make a selection. But at the end of the day, he communicated that his nurse was sleeping on the job. And she admitted that she was indeed sleeping on the job. So through the system, he was able to achieve the care that he truly needed. Now, he perhaps would have had even better results had we got him earlier in his heyday. If we look at that motor imagery or mu-based brain-computer interface, it turns out that people over the age of 25, female, and play at least one musical instrument and not on effective medication or drugs. And effective drugs there being, are you on something that changes your ability to focus? Is it a stimulant or a depressant? And that could be a B12 vitamin. So someone who plays a musical instrument, quite understandably, has better hand dexterity and presumably can even imagine to such great granularity the movement of their hands. So when we ask them to think of opening and closing their hands or things related to that, they are much better at generating that stronger level of activation than the average person who may not have that training or have refined that pathway. The last area for functional infrared that I described, people who are mid-60s or younger, so we do have thresholding found within our tests, at least a level of high school education and doesn't consume caffeine regularly. And we'll pause and think, who is that in the world? Yes, there are people that are not addicted to drinking coffee or consuming caffeine in a regular fashion. So it's interesting to see these correlations, which might help us better understand our populations as we're testing with brain-computer interfaces. Because we put sensors on individuals, but it's not just the output in a vacuum. We need to understand the context, and that context is the human being and what are their experiences. Because experience does matter. Here we're seeing an example of novice versus experts, and in this case, in a sales situation. So at the Kennesaw State University, we have the Brain Lab, but we also have a nationally renowned sales center. And we're training students to go out and engage in more personalized moments with their customers. Well, there is in fact a difference between someone who's been doing this for several years or teaching this versus someone who is new to this. Again, we think about learning context, this is something natural that we would understand. However, we can see it in the brain. And so here, the individuals are watching a video of the initial sales approach. So this is when you come in and you meet your customer, you meet and you greet them, and you get to know them a little bit. So just the first part of that segment. And they're watching video of this happening. And we don't give them any further instructions and just say, just watch. And then we're seeing what their brains are doing. Interestingly, as we average over the participants, we see a distinct difference. And so in this case, just looking at 8 electrodes, as we focus more on the executive function, we're seeing the area that's most associated with working memory, so that center electrode, that center channel lighting up for novices, versus our experts are not exhibiting their highest levels of activation there. So red being the highest level of activation. Instead, for our experts, we're seeing more of that activation over, yes, the Broca's area for language. So now we overlay this with actually talking to the participants and understanding what were they thinking about, what was their experience as they watched. For novices, they did not know what they were watching. So trying to make sense of things. And that would be indicative of higher cognitive load or just trying to work things out. For experts, however, we're seeing perhaps an example of neural efficiency, where someone who is an expert in something, if you are judging something in which you're an expert, you have reduced level of effort needed. And so that area associated with working memory is not the highest area of activation. Instead, they talked about listening to the exchange and hearing what the customer was saying, what the salesperson was saying to the customer, and that there was a lot of focus on that conversation. So it does make sense, even though they couldn't see these pictures that we generated post hoc of what happened, that it confirmed, in a sense, from their own words. Well, we're doing just a number of different things. I am, at this time, happy to discuss the array of projects. But my biggest takeaway is, one, understanding the individual differences between our participants and keeping our recordings, our results in context. But two, appreciating that there are a number of different ways that we can apply brain-computer interfaces in active or passive form, real-time out in the field. So there's amazing work done in the clinical setting, but there's also amazing work to be done out in the field. I was very conscious, Christoph, of trying to keep within my time and not extend out too far. So at this time, I am happy to take questions if you have any.
So thank you very much. This was very nice. And if you just click on the Q&A button, you can also see the questions. So the first question is, F nears 8 channels and EGP32 channel combination is compatible to tap the biomarkers for DLFC of or decision-making tasks. How many channels minimum would suffice such experiments? Any opinion on that? How many channels would you use for decision-making experiments?
Well, if you use our paradigm, we're looking at literature. And so we're not trying to recreate the wheel or figure out someone else's work and mapping different areas that are related to decision making. We found that a 16-channel bioamplifier has been sufficient to have a range across the head for understanding areas of activation.
Okay, then the next is from Badra. I'm interested in your project about ADHD treatment using BCI in children. Do you use methods like TES or TMS along with BCI?
Oh, unfortunately, no. We do not do additional stimulation for those participants. For the project with ADHD, that was indeed with children. So in this case, it was middle school aged. For us in the United States, that is around 12 plus or minus years. And the students in that study participated in a brain training game over a month and found that they indeed were better able to concentrate. Their teachers saw that as well, their family members, they recorded it for themselves in their journals, but we could also see the change with their beta theta ratios in EEG.
We're also running TMS studies with our recovery system. That's the BCI system for stroke rehabilitation. And then we apply TMS stimulation of the sensory motor cortex before we do the TMS training. And the same also with direct current stimulation with the purpose to enhance the rehabilitation outcome. So it's definitely useful to combine it. Then we have
Thank you.
A question. We are using NeuroDecode open source for the BCI experiment. NeuroDecode is responsible for recording the data and is loaded with the classifier algorithm as well. We are using PsychoPsy code toolbox, I guess, for experimental design and looking forward to integrate the NeuroDecode with PsychoPsy. Would you recommend doing this? Any thoughts about that? Do you know the toolboxes?
I don't. So for the cognitive load real-time classifier, we have built our own based on recordings. So someone who is much better at machine learning has developed that at the Tech3 lab or Tech3 lab. So that's something that we'll investigate, NeuroDecode. Who is that offered by? And I'm sorry, I'm not able to see all of the
I already confirmed it. So Maximiliano is asking, where can we know more about NeuroClass? Because I Googled it and I couldn't find anything. I'm so interested in work with BCI and JavaScript. I program Arduinos and drones with JavaScript to connect BCI, but I couldn't buy a BCI device. So I guess he's speaking about Google classes.
Yes.
Do you know if they're still available or not?
So first about Google Glass, my understanding is they are not available for purchase currently. If you have a contact at Google, it is my understanding that they are still being used in private in their secret labs, but also being used for specific situations within industry. For example, within factories or with medical applications that people have partnered with Google to have these devices. So it may still be possible to acquire it that way. or through a third party who may just be looking to no longer need the Google Glass. However, the work itself about neuroglass, if you look to, and I can provide this directly as well, proceedings from the NeuroIS retreat is where we shared that work.
Okay, then Pablo is asking, what kind of experimental paradigms do you use to monitor emotions? Are you carrying any studies of BCI for monitoring emotional activity to enable emotional communication?
Oh, that's interesting. For emotional communication, so this is a little more complicated, where we are using surface electrodes. So we are only looking at asymmetry and the positive and negative approach paradigm to this being presented. So if you look, for example, within the alpha band, there's popular work following that paradigm. And so we also are using that as a measure for emotion. Often when we get into emotion, though, it may be needing to triangulate that with something outside of the brain, and that perhaps being from the face and what we're doing, and that's across culture. If you're smiling, of course, that means you're happy, usually. So it is multifaceted, because someone could be furrowing their brow and it not meaning that they're disgusted. It could just mean that the screen is too bright for them, and they're that doesn't have to do with the stimulus itself and how they're responding.
Okay, then another question. The Pope engagement index uses summation of the band powers. Could you please let me know whether these are the sum of epoch, band power, or trials? If epochs are considered, what is the length of the epoch, and how many epochs are considered for this summation?
Oh, that is a great detailed question about the Pope engagement index. How about that's something that I can give you directly? Who is that question coming from?
So it's coming in at 229.
Oh.
So yeah. Do you trigger the data, or is it just free running band power that you're considering?
I'm sorry, Christoph, could you repeat?
So my guess is that you can do both. So you can have a moving average window to calculate the band power to get the Pope engagement index, but you can also average and trigger the data for doing it. And another question is, we are doing speech imagery tasks. How do you think individual differences might affect the results? Did you ever work with speech imagery?
No, we haven't, except for functional near inference. So not looking at it relating to cognitive load. There are human-computer interaction studies that look at talking aloud and how that impacts someone's mentalization of the activity, which I feel like the studies showed minimal impact on what was happening. So that would be ACM SIGCHI is the venue for that work that I'm recalling. If looking to get more information about how actual speech impacts the process, mental process, and how.
So actual speech is much easier to decode because the timing is more precise. So everybody needs a certain time to say one word. If you're just doing speech imagination, then this is much more difficult because the timing changes a lot. There's work from Bob Knight with ECOG electrodes, and they developed a special mechanism to enlarge or extend imagery speech to be able to decode it with the ECOG recordings. So to start with, I would actually use real speech, and from that I would move to imagery speech. It's just easier.
That makes sense. Also recall, I guess, Gervin Schock doing work with implanted and being able to decode speech.
Oh yeah, did you hear the video where he decoded the music?
No.
It's really cool. Then Anatol is asking, could you please clarify, will the P300 Speller Hackathon task be related to the g-tec dataset published in 2009? That's correct. That's about the group study that we did with the P300 Speller, and this dataset will be available besides some other datasets with locked-in patients and patients with disorders of consciousness. But the publication that you are citing is correct. So this can be used as a background reading. So thank you very much. This was a very nice presentation. Also look in the chat. They are saying it's a very good presentation, great talk and so on. So
thank you very much.
So how is your university doing at the moment?
We are still trying to figure out what we are doing fully for the fall. And for folks outside of the United States maybe watching, that we do not have as great of a handle on the virus as others. And that impacting our ability to have face-to-face classes in a safe environment. And certainly as we're all experiencing challenges, how do you proceed with research that wants you to put sensors physically on someone?
Sure.
The data.
It was very nice to see you on Zoom, and I'm looking forward to see you next year in Vienna.
Oh, it will be my pleasure. And if you can join us next door for the NeuroIS retreat.
It'd be nice. So thank you very much. Have a nice day.
Thank you.
Bye.
Bye.
And this was quick. So I can already see Rupert smiling. So you see g-tec members are always smiling because they have too much work, and that makes them happy. Rupert, can you also please share your screen?
Oh, yes, of course. Give me 1 second.
So Rupert will show us now in real time how to do P300 experiments. So this is also important for the hackathon because we have had data sets about the P300 visual speller experiments and also vibro-tactile P300 experiments. So please watch carefully that you know tomorrow how to analyze it. So Rupert, please go ahead.
All right. Welcome, everybody. Thanks for joining. You may recognize me from the talk that Gary was giving previously, so where I was the subject. We just swapped places now, so he will be my volunteer in the online tasks we're doing later on. First, I would like to start with a short introduction, a short explanation. So you see already here the outline of the screen. So I would like to tell you a little bit about P300 experiments. Many of you may already know this, but maybe not all of you are familiar with it. And then we run 2 experiments, a visual P300 experiment and a vibro-tactile P300 experiment. We do some data analysis, load the data, calculate the classifier, calculate averaged evoked potentials. And then we will try the classifier and see some free spelling. So our volunteer will try to control the PCI, and the same with the vibro-tactile P300. Okay, so for P300, what we're using for classification here are the so-called event-related potentials. Event-related potentials, what is it? It's an electrical potential generated from the brain in reaction to an external stimulus. So the stimuli are, in our case, exogenous. So they're triggered by, for example, auditory stimuli or tactile stimuli or visual stimuli. So each time you play a stimulus to a user who is attending these stimuli, focusing on them in a way, you can measure in the EEG this event-related potential, as you see here, one example on the right side. This event-related potential has some positive and negative peaks, and they all have names according to if they're either positive or negative. So a positive peak has a prefix with P for positive, and negative peak has a prefix N, and then the postfix for the naming is just the average time of occurrence after you give the stimulus. So the stimulus would be here at 0 seconds, and then here at 100 milliseconds, we would have the first positive peak. So we call it P100. This negative peak we call N100. Here we have the P200 and then the P300. And as the name of the P300 experiment suggests, we are, of course, focusing on this P300. So the amplitude of the P300 reflects the cognitive processing. The more processing you do, the higher the amplitude will be. And this is what we're using to control our brain-computer interface. So let's assume we present to a subject a train of standard stimuli. Could be, for example, just beeps or flashes on a computer screen. But within this train, with rare occurrence, there's also another kind of stimulus, the so-called target stimulus. And the task of the user is to focus on the target stimulus. So the user will not know when the target stimulus appears. He has to focus on it, and each time it appears, he will do more processing in the cortex, and this processing he has to take elicits a high amplitude in the P300 that we can detect, and so we know that the subject was focusing on the stimulus as soon as we detect a high P300 amplitude. So I show this graphically here. Green would be standard stimuli, and this blue one would be a target stimulus. So assume we play a train of stimuli. The first stimulus presented to the user is a standard stimulus, elicits a standard ERP, as you see on the right side. The next stimulus appears, it's also a standard stimulus, elicits again a standard ERP. Then a target stimulus where the subject was attending to appears, and you see that the ERP looks now quite different at the 300 or a little bit more milliseconds after the stimulus onset. We have this high amplitude on the P300. And this difference between high amplitude and low amplitude is a nice marker that we can train our classification method on to be detected. So of course we need a training because the data of each subject, the timing and the height of the amplitude is different. So we use LDAs or support vector machines to train classifiers. So how do we use this for a P300 speller? Assume we have a matrix of different icons on a computer screen. So in this case, the icons are characters, but it can be any recognizable icons. So also we have here, like for a bell or a loudspeaker, different icons. So now the subject wants to select one of those icons. For example, he wants to select the A. What will happen is that each icon starts, so the icons start flashing one after each other in randomized order. Each flash will generate a standard ERP. But as soon as the target icon flashed, so in this case the A, because the user decided to focus on the A, then the big amplitude in the P300 will be elicited. We can detect this big amplitude and know that the user was focusing on the A and present this as a result of the classification. So by that, you can use the speller to select character by character and start writing sentences or words. A little bit more of presentation, how it looks like. I have here now just for demonstration purpose, a reduced matrix of only 8 symbols, A to H. As I said, let's assume I would like to spell the A. So I focus on the A while all icons are flashing in random order. So let's start the flashing procedure. Oops, I'm sorry, this was too much. Yeah, let's say first a C flashes, generates a standard ERB. The F is the next one, standard ERB. For the G, the same. And now the A flashed in the randomized order. And as you see, the amplitude of the A after the A was big. I could detect it, and I know subject was focusing on the A. To reduce the or to increase the signal to noise ratio, because we know EEG is quite noisy, we play several of such cycles of flashing of all icons and average over the cycles to get to reduce the noise, increase the signal to noise ratio, and then we do the classification after several cycles of flashing. So each time the cycle is randomized, so the user never knows when the target stimulus will appear. It appears each time at a different point of the cycle, so he has to focus the whole time, and this increases the processing, the cognitive processing, as soon as the target stimulus appears. All right, I would like to show you 2 short videos that shows also the visual experiment and the tactile one, and then we go on to the online presentation. So I can make this quite quickly because you will see it right away in the online presentation. So, oops. So this is the visual experiment. You may recognize the subject here. It's Christoph some years ago. We used the old cap. You see here the Simulink model. You will see it later on again. One selects some characters to train a classifier. And what you see now is not that every character by its own is flashing, but each time we let flash one whole row or one whole column. So this makes the whole procedure just faster. So assuming each icon flashes on its own, it takes a while until all icons have flashed once. But if you let each row and each column flash once, then of course you're much faster. Then we get a P300 with high amplitude. Each time my target icon is in the row or in the column that just flashed. And so, for example, for the A, I would know I would receive a high amplitude after the first row flashed and after the first column has flashed. And so I know, okay, my target stimulus is in row 1, column 1. This is the A. And so I can use the same approach. There's some fine-tuning one can do on experienced subjects. So the question is, how many repetitions do I need for good signal to noise ratio? So we start with high number of repetitions, but if you have a good trained subject, you can reduce this to lower numbers, and you can also increase the speed of flashing, the on and the off time of each flash. by that way, we can make it much faster. I will just fast forward here. So this is now like high speed. The subject was able to spell one character in 0.8 seconds, which was, at least by the time we made the video, world record. Don't know if anyone is faster by now. Second video is about the tactile P300 speller. So we use this, we have it in our Simulink HiSys environment, but we also have a standalone application of the same paradigm in the so-called MindBeagle product. So the MindBeagle is for assessment and for communication, assessment of the status of people with disorders of consciousness, and also for simple communication for those kinds of patients. So we used a tactile P300 speller to provide simple yes or no questions. So we place one vibrotactile stimulator on the left hand and one on the right hand. And we can ask a question to the subject and tell him, if you want to answer with yes to our question, please just focus on the stimuli you feel on the left hand. And if you want to answer no, then just focus on the stimuli you feel on the right hand. We tested it in Palermo with one of our validation partners, Rosella Spataro. So we had patients and we asked them questions where we already know the answer they should give. So by that we could of course test if the answer or if the patients have control or no control. So for example, Rosella asked the question, of course in Italian, because it was done in Italy, in Sicily. Am I speaking in Italian to you? So the expected answer by the subject was, of course, to say yes. So I start the video. You see the detectors. Yeah, you don't see much of the detectors, but they're fixed on the left and the right hand. And this is the MindBeagle computer. So the system provides now the sequence of stimuli. It takes a while to have enough repetitions. And after that, it provides a classification. And this lens moves to the left or to the right to provide the answer yes or no to the treating medical doctor or whoever wants to ask these questions. So now soon the sequence is finished. And the lens moves to yes, so it was the expected answer in this case. So to each patient we provided 10 questions and counted the number of correctly answered, correctly provided answers. Results are published. We can share a link of this publication with you, of course. Okay. So just 2 more slides before I move on to the online demonstration. So where is this technology used by g-tec? This is, as I said, we use it for people who are in disorders of consciousness. And I would like to mention here the DOCMA project, an international Marie Curie RISE project with consortium partners in Spain, Portugal, Austria, and many other countries, as you could see. And the goal of this project is mainly to enhance international research and to enhance the network and provide transfer of knowledge, not only to the scientific community, but also to the broad community, to patients or their relatives, and strengthen the network of our collaborations. And of course, we share our scientific findings. So if you're interested in this project, I hope you are, then please visit the web page that I present here. You can see it later in the PowerPoint slides that we provide, of course, too. Okay, let's move on to the online presentation. So I start with the g-tec suite, MATLAB Simulink. Takes also a while until MATLAB starts. Right. You saw this already in the presentation of Gary. So we have here the list of all our models, demo models, and also models of BCIs. So I guess I'm quicker if I just load here from the recent, because I, of course, opened it before. So now I don't have to search for it. Takes quite a while now. Okay, in the wrong folder, so it couldn't load the previously saved configuration. Let me just move to the correct folder where I saved the model. Here it is already. Okay, so this is the model that drives the visual P300 experiment. So at the beginning, of course, we always need data. So we have here the block that acquires the EEG data. You can use it with any of g-tec amplifiers. Let me just start it. I use a g-Nautilus with 8 EEG channels. But as I said, you can use a g-USB amp or g-amp too. So that's the configuration for the g-Nautilus. As you see, we only have 8 channels. With our standard EEG montage for P300 experiments. We just use a notch filter to reduce power line noise, and the signal will be further filtered in the online model. So no filtering, no more filtering is needed here. I just close it. Short explanation of this model. So data comes in here. We just do a data type conversion to double precision. And here we have an online filter. It's configured to, as you see, bandpass between 0.1 and 30 Hertz of order 6. So this is one of our standard blocks that we provide with g-HiSys. You can configure your filters as you need them, and just by plug and play put it into a Simulink model. Let's close it. So this is just a downsampling of a pre-processing step, not of more importance. And you can do some configurations in these two blocks. So buffer length, we always keep to 800 milliseconds. The number of flashes means the number of repetitions we use until we do the classification. So the number of cycles we play and average to increase the signal to noise ratio. In the training, we keep it on a high number, and later on we can try to reduce this a number of repetitions to increase the spelling speed. But to train a classifier, we anyway need a sufficient number of trials that we can calculate a proper classifier. So I keep this also as at the settings as they are. And here, in this window, we could also fine-tune the timing. So the flash time, 100 milliseconds means how long is each row or each column flashing on. And the dark time is the time in between. So if I would reduce these two values, then the whole paradigm would be quicker, would be harder to focus on, but the spelling speed would increase again. And we have here two modes, the copy spelling and the free spelling. The copy spelling is necessary to acquire data for a classifier. So for that, the system needs to know on which symbols the subject was focusing on. In the free spelling, we don't know it. In the free spelling, the subject can just decide on which icons to focus, and the system just provides the result that it classifies. So then we have also here two scopes. The G-scope will just provide, will just show the raw EEG, so we can check if the EEG signal quality is fine. And then we also have this EP scope, which is very nice. It shows averaged ERPs. So it takes the target and the non-target trials and averages them, of course, only in the copy spelling mode, where it knows which one was target and which one was non-target. So in the free spelling mode, this is not possible. And here we just save the data for offline analysis and for training of the classifier. So in the block, you just select a file name and just keep it in at session 1. And that's it. Let me click on Run to start the model. And in the meanwhile, I could ask Gary to take a seat, please. Hello again. Nice to see you again. I just opened the G-scope. We don't see much because the EEG cap is not yet on the head. So of course this data is not valid EEG. Okay, we have to make sure that the CZ is right in the middle between Nasion and Inion, which is on the back side of the head. And since I'm pretty experienced, I already got a good feeling how to do it without a measure tape. But if you want to make sure to have it correct for a proper study, you better use a real measure tape. But now for this demonstration, of course, we don't need that much of precision. So we inject gel. These kinds of electrodes are slightly different to what you have seen with the FNIRS EEG combined system. They are called ladybird electrodes, but they have the same technology. They have a preamplification in each electrode to provide a very good signal quality. And we don't need abrasive electrode gel as you would need for passive EEG electrodes. So I have different kind of syringe, but also quite similar. You move into each hole of these electrodes, move away a little bit the hair, because of course we again need contact between the skin and the electrode. And then I fill up just each electrode with electrode gel. Also, never forget the reference electrode on the earlobe. Sorry for this short interruption. I had to refill the syringe with more gel. In the meanwhile, if you watch the scope on the screen, you see already that I have gelled the first 5 channels properly. You see a nice EEG there, and the rest of the channels will follow soon. Okay, let's wait a little bit more. So number 7 maybe needs a little bit more of gel. I will just try to move the hair also more out of the way. Gary is a young man. He has a lot of hair on the head still. Also number 8 maybe needs some treatment. So what you see, this drifting on number 7 is just because of the filter. The high pass at 0.1 hertz. It needs some time for the transient. So each time you have big changes, like now I put the tap on the electrode. This was number 8. Okay. You see it start floating because the filter, when you have a big jump in signal, the filter needs a while to come back to normal level. All right, EEG looks very good. Let's do some quick tests to make sure it's good, as we did before. Could you please blink your eyes several times? So you see, especially on the first channel, the biggest changes in amplitude. This is because the first channel is the most near to the eyes. And of course, the more we are near the eyes, the more the movement of the eyes will be visible in the EEG. If he clenches his teeth, we will see it probably on all channels. Very nice. Yes, thank you. So this looks like very good EEG. We can continue. Sorry. Okay. I'm sorry, this is now free spelling. I said I need copy spelling. So let's just stop it. Okay, change back to copy spelling and start again. Yeah, now that's better. You see the matrix, and in the copy spelling, we have to tell the user on which icons he shall focus. So usually we use a 5-character word for training. So this will provide enough trials to calculate a proper classifier. So let's spell g-tec. This is now 4 characters. I need a 5th one. Let's just take g-tec 1. So as soon as I click start, this is the row column speller. So the rows and columns will flash in random order. Gary is supposed to follow the sequence of characters as provided on the top. And between the characters, there will be a short break, and the system will show the subject, will show Gary which character he should focus next, so that he will not get lost during the paradigm. So Gary, are you ready? Then let's start. So first character to focus is the G. He will only focus on the G. He does not know which or when is the row or the column where the G is written will flash, but each time it flashes, he produces the high amplitude in the P300. And we hope we can detect it and train a proper classifier that we can use then for controlling the P300 speller. So each row and each column flashed now 15 times in the random order. Now the next character is the T. He only focuses on the T. Again, they're flashing in random order. He never knows when his character will flash. The system, by the way, as you see, it already tries to classify the results, but the classification actually is wrong because I ran the model previously with empty data and trained a classifier on it just to test it. So now the classifier does not fit at all to Gary's data, and it will just classify nonsense, let's say. So don't mind about it. It will write again wrong classifier, wrong character, of course. So it detected, it classified the X now instead of the E. So in the top line, you see the target that you should focus, and in the bottom line, you see what it detected. And for the last character, which is the 1, all right, so the training is done. We acquired data. Gary, may I ask you to switch place? So since we have a wireless amplifier, it's not a problem that Gary leaves the chair. It's more a problem for me because my headset is cabled. Okay, so let's start our GBS analyze. I could start it also via the G Suite, but you can start it in the command line of MATLAB. This was just not the quicker approach. So this is the window of GBS analyze. I want to load the data that we have just acquired. It must be this one, yes, session 1. I have to enter the sample rate that we just used. It was 250 Hertz. All right, so this is the raw data in the background. What you see here in the foreground is the automatic batch starter. So GBS Analyze presents when each time you load data that was acquired by a g-tec Simulink model, it usually knows which kind of data it was. So it knows, okay, I loaded P300 data. So it suggests me different kind of batches, scripts that I could use on this kind of data. So if I use another model, SSVB or motor imagery or whatever, it would suggest me different kind of batches that fit to this kind of data. Let me just cancel it for now because I want to just show you the data. We can go back to this later on. You see here the acquired data. It looks quite flat. This is because GBS Analyze shows each channel according to the minimum and maximum amplitude. And in the beginning, our filters were floating. And this means you have this initial transient floating around. And so viewing this, sorry, doesn't make much sense. So let's just change the scaling. So we have here 11 channels. Channel 1 is the timestamp that we can remove. Then we have channels 2 to 9 are the EEG channels. And channel 10 and 11 are trigger channels that I will explain in a minute. So I just want to rescale the EEG channels, which is channel 2 to channel 9. And I prefer a scaling of plus minus 100 microvolt. Some people prefer 50, but that's up to you, of course. I click on apply and you see it updated here. And so I can close this window and have the scaling changed. So now you see this initial transient of the EEG. We can scroll scroll through the data via the slider. And what you see here on the last 2 channels is just the trigger information. Channel number 10 provides the so-called flash ID. It provides the information which row or which column just has flashed at these specific time points. So here it looks like 3 or so. So it's row number 3, for example, and so on. And the last channel is the so-called target channel. So we had the copy spelling mode where we know on which characters Gary was focusing on, attending on. And so each time this target character was flashing, the target channel goes to 1. And by that, we know we can cut the EEG data accordingly and separate to one pool of target trials and one pool of non-target trials, and feed this into our LDA classifier to detect in the free spelling mode the according selected characters. So let's have a little deeper look to the EEG. It all looks nice. No noise. Quite good. So now we can trigger the data, and then we can calculate averaged ERPs. So for triggering the data, we should first read out the class information, which is the sequence of non-target and target stimuli. And for this, you need a little bit of, you need some MATLAB commands that I don't want to show you in detail because they are described in our instructions for use. So don't worry if you don't know what to do. You will find everything in the instructions for use that we provide with GBase Analyze and GHISIS. So it will guide you through all the steps necessary to calculate or to do these calculations. So I copied the commands just here, and let me just execute them, and then we save some time for the more interesting part. So now we can go on to trigger data. I go to transform and trigger. And what we usually do is to also cut a little bit of a baseline that is just the 100 milliseconds before the stimulus appears. And we use this baseline to make a baseline correction, which means we can bring each trial to 0, to the baseline, which is important when you average trials. You have to remove the DC component of the EEG. So what I do is to say, okay, let's, for each trial, use 100 milliseconds before the trigger. And then usually we take 700 milliseconds after the trigger, which is for sure sufficient. Usually the P300 is, yeah, it's 300, 400, maybe 500 milliseconds after the trigger onset. And we trigger now on the channel number 10. So each on this flashing ID, for each time a flash appeared, we cut out the segment of EEG 100 milliseconds before the flash and 700 milliseconds after the flash. So I select physical channel I want to trigger on. It's the number 10. I want to trigger on the rising edge and to get numbers between 1 and I think 10 or so. To get all numbers, I just put the threshold lower than 1, but higher than 0. And we also need to accept the overlap because the segments of EEG will overlap now, and it should not discard overlapping data. It should just cut each of them separately. And this is why we also select this incomplete. I click here on add to list. I could select in this field several kinds of triggers. I could also trigger on other information, but this is enough. And after the triggering, I don't need the trigger channels anymore. So I can say, okay, exclude number 10 and number 11 after this operation. And we also exclude the timestamp, which is on channel number 1. And what stays will be number 2 to number 9, which are just the EEG channels. Click on OK. So now I just have selected which channels to cut away, and I have to apply just the operation that I programmed here. Click on Start, and now the data are triggered. And so I have now single trials. You see T2, trial 2, and so on. And we got, let's scroll to the end, 900 trials. We don't have the class information loaded yet that I calculated before. So we don't know which was a target or a non-target trial, but we can just load this class information. I used the import wizard. Again, don't worry if this looks now complicated, but every step is explained in the instructions for use. So I select just the calculated information, click on Open. I have to confirm here. And now I know from the instructions for use that this attribute number 3 will be the non-target trials, and attribute number 4 is the target. And that's it. We have now triggered EEG data, 900 trials marked either as non-target or target. We have much more non-target, of course, because the target appears just in rare cases. And now we could jump through the single trials. Here's a target. This is a non-target, target, non-target, and so on. You can go through the data and look for artifacts now, but Gary behaved quite well, so we don't have artifacts, I believe. Oh, here a little bit maybe. No, not really. But let me just demonstrate, assume there would be a big artifact on trial number 24 that I don't want for my further calculations. Then I can mark it in GWS Analyze. I have here the markers and attributes. There are some markers to mark channels that are bad, and there are markers to mark trials. So I know this artifact is a marker for trials. I click on it, and now I could say, okay, trial number 4, let's say it's an artifacted trial. I click on the EEG, and you see here now it got this additional information. It keeps the non-target information. It was a non-target trial, but it's now also marked as artifact. If I would click again on the data, this artifact is removed again. So let's keep it. Let's say trial number 24 was artifacted. All right. We need to do the baseline correction, and then we can calculate the averaged ERP. For the baseline correction, I go to pre-processing, click on baseline correction. So we triggered the data 100 milliseconds before each stimulus. And this is the information I just enter here. That the baseline interval is the 100 milliseconds of each trial. So we start at one sample, which is 4 milliseconds, because we have the sample rate of 250 Hertz. If I would change one value, then you see the other value, the samples go to 6. And if I change the samples, the milliseconds change accordingly. So let's go back to one sample, starts at one sample and stops at 100 milliseconds, which is 25 samples. And apply this baseline correction on every single trial by just clicking on Start. And now we can do the ERP calculation. Here we are, average under Analyze. So here I can average trials. Baseline correction is not needed anymore. We did it already. So now I specify the averaging options. And this is nice. I can say I want separate averages for separate classes, different kinds of classes, because I have marked my trials as non-target and target. And I want to have averages of all non-target trials and averages of all target trials. So I selected this, and then here I removed, select the kinds of classes I would like to average. This is non-target and target. I don't want the artifacts and not the remove. So now it would take all targets and non-target trials, but I have marked one trial to be artifact. I don't want this trial to be in my averaged results. I click here on select trials and channels, and I can specify to exclude certain kinds of trials. I can exclude trials or channels. So I want to specify to exclude all trials that I have just marked as artifacts. So I can exclude or include only. I use exclude artifacts, and that's good. And it shows me, okay, one trial out of 900 is selected as artifact and will be discarded for the calculation. I click on OK, and everything is set up here. So we click on Start. And it calculated the earpiece. To be fair, I talked all the time while Gary had to focus on the target, so I guess it was pretty hard for him to focus, or do his smart guy, but it's not so easy. I just changed the scaling of the earpiece to -10 microvolt until +10 microvolt. And yeah, there's not that much to see. As I said, I would say this is because of the bad conditions. So you see here interesting negative peak quite late. Here's this must be the P300, quite small. Let's change the scaling. Maybe -5, +5, and apply. Yeah, so here we have a small P300 here again, and here we had maybe some noise. Yeah, the environment was not perfect. It was more or less a no-go to talk all the time, but it's a demonstration, so of course I had to talk. Okay, anyway, let's calculate the classifier and see if it works anyway. So I should hurry up a little bit. I just load the data again. And then I use just this automatic batch starter. That will pop up. I can say I can calculate LDA or support vector machine classifiers. I just select to calculate a simple LDA classifier. I have a single file. It will calculate the classifier and store it in the workspace of MATLAB. So that's done already. Goes quite quick. Classifier is stored, so we can go back to the model. And let's just switch places again with Gary and make a quick start. Hello again. So time is running. Let's just try 2 characters. Please try to follow the sequence A and B, and let's see if it works. Okay. Quite good. As you see, the system classified the sequence that I asked Gary to do, A and B, successfully. So this time I didn't talk and the classifier was still good enough. So good job. Let me ask Christoph how much time we still have. Should we come to an end? Okay. Let me just show you there's a model also for the vibrotactile P300. It is very similar to the visual one, so there's no need to really demonstrate it, I guess. And again, everything is described, of course, in the instructions for use. So this would be the model for the vibrotactile stimulation, where we can enable these cues. So this is just to help the subject to tell the subject on which stimulus he focuses. We have three kinds of paradigms, one with two tactors, where you put the tactors on the left and the right hand. One with three tactors that you can use for this communication. There is one tactor on the left hand to provide the yes answers, one on the right hand to provide the no answers. And then we need a third one, a distractor that we place on the ankle. This cannot be used for to provide an answer. The ankle for the answering, you just use the left and right. And then we have an advanced model where you use 8 different tactors that you can place, for example, on the fingers, 4 fingers of the left and 4 fingers of the right hand. And then, of course, you have 8 symbols to choose and have a higher information transfer rate. But to be fair, it's also harder for the subject to focus on the correct stimulus. So this model does the same as I showed you in the video. You don't have the visual stimuli, you just have tactile stimuli. We use these tactors and you place them, you fix them with tape on the hands, and then the subject focuses on the stimuli that the subject feels. All right, thank you. I hope there are some questions.
Thank you very much, Rupert. So if you hit the Q&A button,
right,
then I start with the first one. So somebody's asking if the talks are pretty complicated with all the demos. Of course, there are a lot of steps to run a brain-computer interface. It's pretty complicated signal processing and data acquisition. So I suggest you to attend the hackathon, because then you get enough time to learn all these single steps carefully. Then Ridike is asking, what should be the minimum value of the ERP amplitude in microvolt to be considered as ERP and not noise?
Sorry, I can see. Is it the first question?
Rupert, I don't hear you in the headphones.
My apologies, I muted the headphones.
That works. It's the question at 3 o'clock and 2 minutes.
Okay, what should be minimum value of ERP amplitude in microvolt to be considered as ERP and not noise? So this depends a little bit, or it depends on the subject, of course. I would say around 5 microvolts or a little bit higher, then you have a nice ERP, but it could be also lower. It's more important that it's steady. So then you can, you just need to be able to detect the difference between target and non-target. And then the amplitude is not that high importance.
The next one is, does the P300 spelling require subject-wise training?
Yes. Subject-wise means to train the subject. This is not really necessary, so everyone can control P300 speller right from the beginning. So you just need to acquire data of the subject to train a proper classifier for the subject, but then you can control it just from the beginning. That's the nice feature of P300 spellers.
Cheng is asking for the record where a letter was spelled in 800 milliseconds. How brief, fast were the flashes of the rows and columns?
Maybe you know it better, Christoph. So this was your world record video.
The flash time was 80 milliseconds and the dark time was 10 milliseconds. So the interstimulus interval was 90 milliseconds. That's actually a pretty demanding setting, which keeps also your attention. And for me, this works just better than a slower speller. Where can we find the g-tec toolbox?
So we have this g-tec suite, which is brand new, where you have the links to the GBS Analyze and HYSYS and other products, and you will be able to purchase it via our web shop. And maybe Christoph, again, you know a little bit more about it.
Yeah, the web shop will get online in a few weeks. So 1st of August is actually the planned time, and then you can get all our g-tec components from there. Another question is, why do the unicorn brain-computer interface need gel and sometimes not?
So we have dry electrodes and gel-based electrodes. And of course, the dry ones, as the name suggests, don't need gel. So they directly touch the skin, the scalp of the subject, which is nice. So you spare the time of setting up the EEG, but you have to consider that the signal quality could be a little bit worse compared to gel-based electrodes. So it depends on your tasks, on what you want to do. Depends on if you choose to purchase a gel-based or a dry.
The unicorn is actually using hybrid electrodes. So you get the choice between recording dry or wet. There's a little hole in the middle, which allows you to also do a wet recording. Then Anatol is asking, can you transfer the calibration data from a P300 experiment to another person?
Yes, you can do it. We also use this kind of generic classifiers, as we call them, where you generate a classifier from a pool of data from different subjects, and it works sometimes pretty good, sometimes not that good. So it can work on a new subject, but some subjects have more distinct EEG data, and then it works less good. And of course, it's always best if you can train a new subject-specific classifier for each one.
This is, of course, the case for healthy controls. For patients, the P300 response is very distinct, and you should always retrain. And key is to train as quick as possible, especially with coma patients, because they don't have so long awareness. Ruben is asking, which is the reason for the data conversion block at the start of the Simulink diagram?
It's just we converted to double precision because then MATLAB always works with double precision data.
The reason is that the biosignal amplifier sample with 24-bit, and we transmit float 32 to Simulink, and afterwards we want to work with double precision, otherwise you get rounding mistakes. Why during the electrode setup you observe the EEG signals instead of checking the impedance?
Well, it's because let's say I'm used to this approach. I'm pretty experienced in EEG, and to me this is quicker to really watch the EEG, and I can make sure that the signal is real EEG in a quick way.
Beside that, impedance measurement was developed for passive electrodes. So in the last century, passive electrodes are not used from us anymore for more than 15 years because the performance is much worse. And with active electrodes, you get also a nice EEG recording even with 100 or 200 kilo ohm. This means impedance measurements are completely useless if you use proper equipment because they can deal with very high impedances. And if you look at the BCI performance that we get with active electrodes, it's roughly 10% above of passive electrodes. So forget the impedance measurement for proper equipment. It was developed many, many years ago for passive amplifiers, so useless nowadays. Ridika, I want to know more about the baseline calculation you did.
Yeah, as I said, this is just to remove the DC of the trials if there's any DC component. So, for example, if the filters are having this transient, you have maybe positive or negative DC part on the data, and if you average trials that are not that have a DC part, then this will be in the averaged ERP, and it will also be higher or lower and not around the baseline, the zero line. And so with the baseline, we just calculate the average of this 100 milliseconds before the trial and remove this average from the whole trial, and that way we bring it back to the zero line, each trial individually.
Okay, so thank you very much, Robert, for the nice presentation.
My pleasure.
And we move over to Daniel Strauss. Daniel, can you hear us?
Hi. Can you hear me?
Yes, very nice. Do you have koala bears around you?
Yeah, not necessarily koala bears, but I know you like nature too, climbing mountains, hang out in the woods and all that. So this talk will be a little bit related to this.
Looks more like monkeys, not koala bears.
Yeah, they are monkeys.
So Daniel Strauss is from Saarland University, a very nice university in Germany. And he's doing a lot of work for many years with single sweep ERPs, which are really difficult to do. And he's just active in many different domains, like working for car manufacturers to optimize the vehicles and so on. And we are very much looking forward to your talk.
Thanks. You see my slides, right?
Yes.
That's good. So then you see my group, and probably just from that picture, you cannot really see that we worked a long time with g-tec. There are many cabbies from g-tec, EEG cabbies. So what you also see is that we have since a couple of years a new line of research, which we call remote psychophysiology, where we use camera systems to assess emotional states. Adrian was talking a little bit about this topic as well. I have some slides for that too, but as past experience is telling me, there will be probably no time to really talk about that in detail. Because the topic today is really nice, it's decoding spatial auditory attention using a vestigial pinna orienting system. And the core of my talk is this one study, which is actually, accidentally coming out this week in eLife. So it's probably published today, or it will come out this week. And it shows the topic just here in this talk, because we talk about brain-computer interfaces. I want to put this study a little bit in a larger framework of BCIs. And beside all the engineering aspects and BCI-related issues in the talk, I would be happy if you take something out of that talk beside engineering, because I want to convince you, that we humans also try to move our ears when we try to focus attention. So I hope that after this talk, you will think differently about your ears and the ears of your beloved ones. And what I realized as well, I told you, for people like me and Christoph, who like to hang out in the woods, being in the nature, or spot animals, it's a lot of fun to really observe how animals pay attention. After this talk, it will make a lot of sense to you that, take the laser pointer, that here our baby is turning the head, the chimp as well, but the dog not. The dog is just turning the pinna. So, and just to make sure, I really want to talk a little bit about serious science. So I don't want to talk about this type of ear movements that you may have seen before. Maybe you can do this as well. Those are voluntary ear movements. This is, of course, not what we talk about. We talk about ear movements that happen automatically when you pay attention. So, and as I mentioned before, I want to put this a little bit in the more broad BCI framework. And where we start, it's always to talk about hearing. It's a good old cocktail party problem. So, and the cocktail party problem is basically if there are a lot of speakers and you have to focus on one, and people like us, we are interested in how the brain is actually managing this situation. And nowadays, this is important, to adjust hearing aids, because a lot of people complain they have this modern digital hearing aids. There are a lot of options to adjust them. But still, if they go to cocktail parties or similar settings, where you have a lot of competing speakers, they're just tired afterwards, and they don't like the device, and we just try to improve the situation for these people. Actually, this image here was taken in 1961, so a long time ago, and talking about primate evolution. And in this talk, you see it's kind of funny. Please spot the gender separation in this image. That's kind of funny. But anyway, I put this guy a hearing aid that you can see here. And one way to help out in these cocktail party situations is that we use directional microphones. So we have microphones that ideally amplify the sound source in which you are actually interested in. But, at this moment in time, it's just the way in which you look, it's just directed to the front. So I orient here, so I want to focus attention to this woman or this guy. And, it's a little bit difficult because basically you are stuck there. So we want to have some flexibility inside this concept, saying I pay attention here and to this guy, and then the directional microphone turns over here. That's kind of the concept. And I told you the problem at the moment is you're just in this direction. And this concept, we can put this even in a more or in a bigger BCI picture of human-machine interaction. And what we had there before, Adrian was talking about it, you know, talking about BCIs, you saw a lot of talks on using them in rehabilitation. That's kind of the, you know, the classic application, but in recent years, there's a lot of interest in taking this BCI technology to everyday life. It's like a natural evolution, you know. In the past, we used these keyboards to communicate with machines. We still do it now, but we just had this option in the past. Then there's a mouse, cell phone touch. Now we have speech, you know, Alexa, Siri, and this type of stuff. And in future, we want to read out directly what is going on, and the machine should ideally follow the human intentions. So problems that we have is, unfortunately, in human-machine interaction, we know about this love and hate relation to technology. You know, the machine ideally should, you know, anticipate what the human is going to do, but also the other way around. Otherwise, it becomes really annoying if the machine makes decision and we don't understand why. And finally, there's no second chance. You know, if it doesn't work, you just switch it off. To give you one example, for instance, if you there's one autocorrect feature, and you use it and it doesn't work, it's just messing up all the time your stuff, you just switch it off, you know, you never try it again. That's kind of a relation that we know, and therefore it's important that the human can also anticipate what the machine is doing. And what we learn from this for our hearing machines, let me call these little hearing aids now hearing machines, they should certainly not do random stuff, means, you know, making a decision and the user is not satisfied. This happens if we talk about this directional microphones. I told you they are kind of stuck in one situation, and there was the idea around, well, if there's a sudden abrupt sound, they should move over there because probably that's important, and we should pay attention to that sound source. But now imagine the situation, you're sitting in a restaurant and there is a door close to you, and the door is opening and closing all the time. All the time your directional microphone is switching to the door. You can imagine that this is pretty annoying. So we try really to avoid these situations and develop systems that really follow the user intention so that interventions are as natural as possible. And our approach to this problem is, we call it neuro-cybernetic hearing, which is basically, you can translate it now by brain-computer interface hearing aids, is the estimation of one attentional effort vector that has an intensity but also a direction in space. There's much more involved. You know what happens if there is suddenly something coming up in the scene that needs attention because you know, it might be dangerous for you, and how to solve all this, how to include emotions. We work on that too, but that's not what I want to talk about today. So coding intensity, I cannot spend, unfortunately, much on that topic. Also, Adrian was mentioning the cognitive load. Here we call it the listening effort. So we want to reduce the listening effort. That's the attentional effort involved in hearing. In the last 10 years, or I think the first publication on that we had was in 2008, using EEG to analyze listening effort was in 2008. Yeah, so we work on that for a long time, and I don't want to give you the details, but what is really interesting is that this technology really translated. So there's this hearing aid company, Sivantos, maybe if you don't work in the hearing aid field, you may not know this company, but they bought Siemens hearing aids, so it's a bigger company. And they really use now this technology, you know, to assess this listening effort. That's the intensity of this attentional effort vector that I mentioned before. So they use it to see whether a hearing aid adjustment is nice or is not nice. We started, as Christoph mentioned, we work a lot with ERPs, and we started with the ERPs, but in recent years we try to just use, you know, ongoing speech to assess listening effort while hearing. There's also some theoretical concepts where we try to understand what dimensions this intensity actually has, you know, having this internal effort, which is more working memory related, probably more to the cognitive load direction that Adrian mentioned before, and externally to segregate different sound sources. So this was work from the past, but again, it's nice that it could be translated to real application. But now I want to talk about decoding the direction. So that's our topic today, means the direction of attentional effort in space. And we have two approaches or two projects. One is using EEG. So in EEG, there's one pretty prominent approach, which is stimulus reconstruction. This just says, suppose there are 4 different speakers and you are listening to them and then you focus on one. This approach just says that the envelope of the speech to the speaker on which you're focusing is more reflected in the EEG. So the EEG follows the attended speaker, or better, the envelope of the attended speaker. And well, it's interesting as well. I cannot spend much time with this, but we use the 128 channels. We use the HIAM system from g-tec for that, and decoded attention in the 4-speaker free-field setting. Our collaboration partner in this project from outside is Stephen Hilliard from the University of San Diego. These guys are from my lab. And well, Ronny Hannemann was also involved here. He's from Sivantos, as we just saw. So EEG, I think there will be not much time today to talk about it. The publication I came out last year or so, where we really tried to test the limits of this approach, and I think it was the first decoding really in this free field environment with 4 different speakers from different directions. But today I really want to focus on a different approach, which is the EMG. And it's funny because we found that actually by checking the EEG data, and there was it looked like an artifact, but it was much nicer related to spatial listening than actually all the EEG stuff that we tried. And we were wondering, what is that, or what can that be? And then we started to analyze those ear muscles that I'm going to talk about now. So that's an important message. I was talking a lot, and I hope you didn't miss it. I want to talk about EMG today, not EEG, EMG. So, and this is how it looks. There are 2 setups for the EMG measurement. So the muscle activity, we record the muscle activity of ear muscles. There's this integrated technology demonstrator. I will talk about that at the end of my talk. But here, first I want to talk about this, which is a little bit bigger setup in our MindScan lab, where we use camera systems as well, and have a way detailed measurements. Here are 4 USB amps used for this study. You know, there's the stereo vision, we have the heat cam. This is all happening here. This technology demonstrator, a small system, you know, that you take somewhere, you place it, and now say just go on and decode attention, where people spend attention in space. So, and that's the interesting aspect, because when we found these muscle signals, and I knew, of course, there's this pump response, you know, like a reflexive response, you clap and suddenly there's a muscle response. This is known, and it's known as sometimes messing up EEG measurements, but how can it be related to spatial attention? Then I found this paper of our collaboration partner, Stephen Heckley, who suggested in 2015 that this could be, you know, all these ear muscles is kind of a vestigial system that's there from the past and could still try to orient the pinna a little bit. And so we try to follow this approach. But a little bit on the background. So we have these guys here. So this one is that one. Those are nocturnal animals. So they're active in the night. And here you see the eyes are fixed and the ears are pretty large. And these guys can really move them a lot. You know that they have very strong ear movements. So, but in evolution, so if we go here, for instance, the New World monkeys, the ears became smaller, became more rigid, as you can see here in the case of the gorilla. And doing a detailed literature study, what Stephen suggested is that we lost the ability to move the pinna, to move the ears, maybe 25 million years back in time. So when there was a separation from the old world monkeys to those species here. So that's the background, and this is what I actually also like a lot in this study. So, and the muscles that we are going to monitor is here the anterior muscle, the superior muscle, and the postauricular muscle, and the transversal muscle, which is up here. But you will see more carefully, I think, more clearly when I show you where we placed actually the electrodes. So we say we have this neural fossil in our brain. But now here comes the cool stuff. You know, here in Europe, we call this stuff where we use digital systems to revolutionize certain areas of technology, always 4.0. So we have a pinna orienting 4.0 if you use this vestigial system to orient directional microphones. So we lost that ability, but now we can have it again. Whether this is just useful for hearing aids or also hearables, you know, wearables that you wear like a hearing aid to have better hearing, also for, you know, non-hearing impaired people we will see in future. And the methods that we used, we had 5 experiments. You know that there were some voluntary movements where we just try to see what is actually going on in these muscles if we use surface electrodes. There are just a few to non-EMG recordings of some muscles that I'm going to report. Therefore, it was just, you know, important to see what is that actually. And we had a study on emotion as well, but I will not talk about this. We had the exogenous attention, the endogenous attention, and we analyzed something related to the startle reflex. But I just want to focus on these 2 studies today. This is also what we have in this eLife paper. So it's all just on attention. And these are the participants. So we had 28 participants in total. There was a younger group, an older group, and the experiments I will explain next. There's just a note on experiment 2. There were just 21 subjects. That's because we needed to change the paradigm, the entire protocol, after the 8 participants. So therefore, there is a smaller number. But important to realize is that we didn't remove any of the subjects. So all the data that you see has no filtering of whatever. There's no picking of subjects. It's just that the first 8 subjects were removed from this one group because we needed to change the paradigm, adding more speakers and so on, because we saw there's really something happening. So that's the EMG and electrode placement. This is how the electrodes were placed. This is what we used. Pretty tiny electrodes, especially for the thumb. That's the upper muscle here, and a little bit larger ones for the other muscles. And those are the technical details of the study. It's important to realize that we also got data from the neck muscle. We also had frontalis rheumaticus, but this was mostly because of our emotion study, and these voluntary movements, just to learn more about the muscles and check relations. We also recorded the EUG just to see what is the relation to eye movements. We know from literature that we have this Wilson phenomenon, means if you move your eyes a lot, you have but really a lot, and you keep them somewhere arranged here, that you have then activity in the postauricular muscle. So, but the subjects, they had a chin rest, as you will see. They had to look at the fixation cost, but there will be more details when we talk about the studies. Here you see this arrangement, the chin rest, here the camera systems. This was for the calibration of the cameras, and those are some details how we acquired those movies that I'm going to show you as well. So the movie recording is because I want to show you that there's a regular relation between really the muscle activity and some tiny resulting movements that you can visualize. Mysterious Bate case, what this means, you will see later. That's a lady who had particular strong movements, and I like to show you her video, what happens with her if she pays attention to stories. There's another funny anecdote. You see this? We had to set up this lab for this study in kind of a new building. So there wasn't a lot of infrastructure, or it was not connected to our NAS system, and everything was new, and there was a lot of data. And we had this, the 10 terabyte Ironwolf hard disks just lying there like those floppy disks that you had in the past. This was kind of a funny experience for me. So that's the exogenous experiment. We had the subject sitting here. The speakers are arranged like this. And, they had to read the boring text in front of them. As I said, the head was in chin rest, so they should relax, read the text. And suddenly there were some sounds appearing from somewhere in space. A dog barking from here, a cell phone vibrating from here, a mosquito coming in from here. So this is what happened. And the sounds had different durations, as you can see here. There's the stimulus interval, and they were randomly presented from those speakers. And well, we had to add a little bit power for one sound because we had to balance it. So in each of the 9 sounds was repeated 4 times, means 1 from the speaker. So this was the exogenous experiment, experiment 1. There's the second experiment, the endogenous experiment. So here we had stories playing. They were from a German course, how to train you to get better in German. And they had approximately 5 minutes duration. And they came always either from the front or the back. So the subject had 2 stories from here, and they had to focus on one of these stories, for instance, on this one, and ignore the other one. Or we had a situation that the stories are coming from here. They had to focus on one of these stories. To increase a little bit the motivation of the subjects, that's important. If we talk about attention and effort, it's really important that they are motivated so they could choose between different stories, like Boris Becker winning a tennis game at that time, and what was the history of the Zeppelin airship, something like that. So they could pick between very different stories, and then they had to focus on one of them. There were multiple choice questions just to see whether they really, were listening and participating in the experiment, and so on. And they should again avoid movements and all that. So the signal processing is just short here. It was a standard EMG filtering. We do it here in Europe, and there was the envelope computed of the EMG. We had a segmentation for experiment 1, triggered to the particular stimulations. We used tight wavelet frames implemented by non-subsampled filter banks to get different frequency bands and see whether it works better in this frequency band than in another frequency band, and so on. Pretty much the same processing was applied to the endogenous experiment. We just didn't segment the data, of course, in the way like we did for the discrete stimulations, as it was ongoing. So, and what we computed here was the energy of the EMG channels. So EMG channel, you take the envelopes and you get the energy. This is basically what we did, so fairly easy. And now we come to the video processing, because I told you we recorded the videos with the hope that we can show some movements and relations to the muscular activation. This is a video clip taken from Michael Rubinstein's PhD defense using video magnification. This technique of video magnification is used to magnify, very small changes in images. Suppose you have this video here and you have an image sequence. Now there are tiny differences between the frames, and with this type of methods, you just magnify these little differences, and you can show the tiny movements that are almost hidden in the original video. So it's the same video here, just with this processing technique. And I thought this might be a nice approach to maybe, magnify some but apparently it has to be small. So for our purposes, we needed to adjust, improve the method a little bit. So we moved from, that's pretty much the work of Philip. So we moved from the Eulerian scheme to Lagrange. We eliminated, and that's very important, the a priori knowledge that we need for the approach that I showed you one slide before, because we didn't really know what we have to expect, and nobody was ever talking about this ear movement. So I was a little worried if we need a priori knowledge to put inside the system, what kind of movement we expect. We might have a bias that I didn't want to have. So we got rid of that and design proper scaling factors to really enhance the movement in the area that we are looking at and compensate for all the global movements, like tiny head movements. We have to get rid of those, of course. And what you see here is involuntary movement. This is just done by a cell phone camera system. That's nothing special. It's just to show you the concept. So this woman is moving her ear. There's a voluntary movement, and here's the magnified version. This was just to start. Does this actually make sense? So, and well, we have already the results of the exogenous attention experiment. So this is what we have. We had these 28 subjects. We had these electrode positions here, and then suddenly there was a sound coming from somewhere, and we were checking the responses of the muscles. And what you see now here, the arrangement is here the ipsilateral speaker, front and back, and here you have the contralateral speaker. This just means ipsilateral. Suppose there's the left ear, the sound was coming from the left, so that's ipsilateral, and contralateral would be the right ear in this situation. So, and here you see the responses from the muscles that we monitored, these 4 muscles. Here the postauricular muscle, anterior muscle, the superior one, and the transversal one. So, and we got the strongest response from the postauricular muscle. Here coming around 50 to 70 milliseconds. And this is important. This is really different from the palm response that, the reflex, like one that you have heard about or saw in the literature somewhere. So there's really a pretty response, and you have the strongest responses ipsilateral on the back side. So if something is coming from the back, that's more interesting for our ears apparently. You see me sitting here straight in the jungle, so if a big animal is approaching from the back, it of course makes sense that I should pay more attention over there, and the ears try to somehow, let the sound in that comes from the back side. So give me clear position. And you see it's a pretty big response for palm, but also for the transversal muscle. So the little one up here and the others as well, just some. So the superior muscle is pulling your ear up. It's not responding very strongly to this type of stimulations. So that's the average then over all the subjects. But I will show you also single trial data soon. If we talk about statistics, there was a careful statistical analysis, and what is important here is that, because we want to talk about decoding, is that I can clearly separate between the ipsilateral and the contralateral direction. Means whether the sound source is on the side of the ear that I'm monitoring or not. In other words, I can classify in this way kind of the direction from where it is coming. But I will talk more about this later when we really have the decoding. So there was an effect between front and back. You saw that from the back side, the responses were much larger, and there was no significant difference for the age group, just that the older participants had a little bit smaller response, means response of the anterior muscle. So here you see the single trial data that I promised you for all the participants, and you see pretty strong responses to all of them. So this is, of course, normalized, but if you zoom in here, you see also here it's a little bit more reddish than in the other areas. And the average here gave us the responses that we saw before. Here you see the responses for our younger participants and here for our older participants. So here's the separation line, and also you see here there's no big difference between these two groups. That's the EEG response. The paper is actually full of this, to exclude different effects. If the paper has maybe 10 pages, the paper with all the supplements has 40, just to rule out all the effects from different muscles. So there's more in the paper. This is just short. There's no regular EEG response and there's no regular response from the muscle, so that you say that's Wilson phenomenon or something else. And here you see a little bit this magnified movements. This looks kind of fancy with the color overlay, but I want to explain you a little bit what you actually see here. So here we have the post-auricular muscle response. And there you see, it gave you the strongest responses before. And here you see the muscle activity, right? That's this red line. So that's the muscle activity. And that's the actual movement. You see here the magnitude of the movement in millimeters, which we detected from our stereo vision camera systems. So you see there's really a regular relation between muscle activation or muscle activity and the response and the movement that we see in the pinna. Here you can spot all the muscles at once. So we have the palm and arm, if they have kind of this antagonist direction. So one was pulling here, the other one is pulling here. Therefore, we put them on one axis. Then you have the transversal muscle here and the superior muscle here. And this is just the total energy from the EMG. And then you see clearly what is happening, what is the dynamics, how the forces are acting on the pinna, if a sound is coming from a certain direction. So this is just that you can really quantify also the motion, but you saw that at the other video already. So let's talk about the endogenous attention experiment. So again, there are these two stories, and you have to focus on one, the one that you like more. And this is what we get if we check the energy from the muscles. This is for the post-auricular muscle, and we see the left channel, so that's the left ear. If I attend left, there's more activity going on here. If I attend right, there's more activity going on at the right ear. So the same happens for the other muscles. And what was pretty surprising to me actually is that this is kind of a sustained effect. So it really lasts for a long time. I wouldn't really have expected that, because I know from the EEG data that we got, if you don't go for stimulus reconstruction, if you want to decode auditory attention, just from the endogenous signal, just from the EEG, and you don't care about the physical stimulation, so you don't use it, decode attention the way that we do in vision, then we know that if other cues are available, voice, modulation, and so on, the spatial cue is actually not that important. And that's what we saw, because it's very difficult, really, if you try to do it with EEG, just you learn now, you have whatever machine learning system, you learn at a certain time, and you should classify in future what is going on. That's really difficult, because if you have many speakers and they have different voices and so on, you can lock on one speaker. But I'm pretty sure that after a short time, the spatial cue is not that important anymore. So, but you see here, that's really a sustained effect for a longer time. And this is what I find pretty interesting. So the same happens for the front speakers, but much less strong. And if we check the statistics, you can also see that we can classify the direction. So that means it's really statistically significant. What I just told you, that if you pay attention to the right, there's more activity at the right ear muscles than for the left ear muscle. This is again just to show you that this happens for different signs. There's a subband decomposition, and you get the best results for this subband, but it even works pretty well for the broadband signal. So I don't want to spend much time with this slide. This is the EOG again. That there's no preferred direction. We mapped the EOG to angles so that we can see how much the eyes move, but it's pretty stable. So they did a very fine job in focusing on the fixation cross in this experiment. And this is the mysterious Beate case that I wanted to show you, the woman who has this pretty strong ear movements. Important to know now, this is not magnified. There's no clear vision, no stuff going on here. That's really the original recording of her ears. And now it's of course a little bit, I'm not sure how the quality will be of the transfer, but what you have to look at, it's anyway difficult to spot all this information that's going on here at once, but what you see here is again this complicated vector plot where we see, the forces that should act on the ear. So I would suggest you to ignore this because this is a little bit complicated now if you see the video just once. But you can spot here the post-auricular response. That's the strongest one. And I recommend you to look, if it works, you can jump between here and here. But if you look at those little crinkles here, you might spot a nice movement of her ears. So I'm going to start that video now. Please focus attention here on the post-auricular response and or the post-auricular muscle activity, that's a better word in here, and those crinkles. So it starts, and you see the ears moving up, and there's still movement going on, and you see the ears really fighting for a longer time to get the information. You see all the ups and downs here pretty well reflected here in the movement. You see there was again a stronger muscular activation, the stronger movement of the ear. Again, those are not voluntary movements. This is really just she's sitting there and listening to a story. And now take care when the experiment ends and she relaxes, you see it moves down a lot. So I find that really an interesting result and a nice video to demonstrate this effect. Not again. So I want to talk a little bit about the demonstrator, but I just have 2 minutes, so I have to make this a little bit quick. What we did for the demonstrator, so we got the EMG from both sides. We decomposed it again using this frame decomposition and classified it using kernel machines, but for each side separately, means for one side and the other side. If you want to know how to optimize these filter banks for kernel-based learning machines, there's an old publication that has all these procedures. And then later we classified just saying that, if there's a learning phase, so the subject has to sit there and we learn, listen left, listen right. We got training data, we train the system, we try to optimize the filter bank so that left and right listening is very nicely separated in this kernel space. And then we apply the decisions and say if both sides say the same, so listening left ear as well as the right ear saying listening left, then it's the left direction, and otherwise it's the right direction. If there's a response, one side is saying left, the other one is saying right, we just say there's a doubt state and we cannot make a decision. So this is how it works. You see now, first we see stabilization on. What it means I will explain later, but here's the task, listening left, and this is how we decode the attention in this experiment. So experiment starts, got nicely the left direction. So there's a little jump to the right. Maybe there was something interesting, somebody screaming, or who knows what is going on there. And we have right listening, and the system moves there. So the same happens now after a minute again for the other direction, and we have again listening left. This is stabilization on. This means the system keeps the direction that it has. It going, in the doubt state, you could say, oh, I don't know what to do, just go straight with the microphone. But here, we really just say, stay to the direction where you were before. If I put the stabilization off, it looks a little different. So this is stabilization off, and we see just much more jumping activity. Those are the doubt states. So where the left side and the right side said something different. And there are many of them, and the longer the experiment runs, the worse it becomes, of course, because we learn at a certain time and then we classify in future. It's very important to keep this causal effect in mind. So it's not that you can do some, if you just do some validation technique where you take data from all the times, then you get extremely nice results, but this is not how it works in practice. And so for learning schemes of different types, you get between 70 and 80%. We even tested in hearing subjects and so on. But again, this is learning. Just connect your USB amps to those electrodes, record the signal from the muscles, and you will see it immediately, especially if you have musicians. You can in real time decode attention pretty easily. And the findings, just to sum up, there was evidence that we have this system that apparently correlates with two sorts of attention. The neural drive to the muscle is weak, but sometimes even movements are visible, and there is sustained signatures of endogenous attention in these EMG signals. And well, this is what I promised you after the talk. I wanted to convince you, and I hope we did. If you want to know more, there's a website to the paper where you can see the movies a little bit more carefully, because again, I'm not sure how nicely it actually worked now. And if there's whatever question, just drop me an email, and I thank you very much for your endogenous attention.
Thank you very much, Daniel, for the nice presentation. It was very informative, and we have also some questions. So if you click on the Q&A button, you see that Pablo is asking, did you study the differences on attention among different emotional valence stimuli?
Yeah, we have this emotion experiment, but the results are not done yet. We are still working on that. So we didn't put different emotional states. This were more, it were not really emotional studies that we had, and stories. Just some was more interesting for some people than the others. But the emotion study comes next.
Okay, then Pablo is asking, have you studied this with music?
No, not yet, but that's an interesting topic. Also, this entire EEG stimulus reconstruction people who work on decoding attention using speech, they study music now, and this would be really interesting as well as using different direction and so on. And we also study how is this actually related to the listening effort, because you saw this video, it looked like the ear was fighting even stronger on one side, but you saw this fight of the ear to get information. And there's, of course, the question, is this somehow related to listening effort?
Okay, and Vinko An is asking which frequency components are strong in the spectrum of EMG?
Yeah, the one that we picked now that I reported was 35 to 75 hertz, but you can go from 20 to 150, you still have a nice result. What is very important here is the decoding that you saw was really for 1 second segments. So that's important if you compare to the EEG and stimulus reconstruction, where we need to have the envelope of the speech. You know, that's much slower because we can sample the EMG activity is so high, it's in a high frequency range, we can really make pretty fast decisions about decoding attention. That's a major advantage for me of this approach. Again, what I showed you was really on 1 second, you know, the movie that you saw, where you saw that left and right direction decoding. These were 1 second segments.
Okay, and what is the sampling frequency you are using for the EMG?
We used here 9,600, but we sampled down to 2,400. But as I mentioned before, the frequency is lower, so you can go even lower. This is a hardware decision question. If we want, of course, to use this somewhere around the ear in the chronic setting, we would go for the lowest possible sampling frequency.
Okay, and some people were asking for your social media contact. Tai Ding posted the webpage from your lab, but maybe you can also post, if you like, your social media, Facebook or LinkedIn accounts into the chat so that people can get in contact with you. Or you can also post your email there if they have direct.
Thank you very much. I will definitely do this. I have to say, I have some folks, they do, you know, Facebook, Instagram, I think, and all that, but I don't know even where it is. So I will, but I will forward this information. Thanks for the interest.
Seems like you're already too old for that.
Yeah, exactly, yeah.
Okay, thank you very much. Have fun with your monkeys.
Thank you.
and this year we don't see us at EMBC, just virtually.
I have some nice pictures, you know, from the 2 years ago version, but no time to show them.
Yeah, Daniel had a very nice Hawaii shirt. This looked funny.
Yeah, I know you were pretty jealous. But I was pretty impressed how you removed the tooth of your son. Probably we can tell that story to the audience.
Yeah, this would be a nice video. Okay.
Okay.
Thank you very much. Greetings to Farah and see you soon.
Take care. Bye.
Bye. So this was very nice, and I show you now something for tomorrow. So tomorrow is the beginning of the hackathon. So we have already a nice timetable. So at 11, David Painter from University of Queensland will give a keynote talk about BCIs. Then we have Martin Walkshofer, who will explain us the Unicorn Brain interface with the whole software environment, how to use it. He will also show us how to do real-time recordings and how to send commands to other applications like the Sphero and so on. Then at 1 p.m. Austrian time, we are doing the group formation so that people get access to the hardware and also to the data sets. At 4 p.m. we have Yannick Roy from Neurotech X talking about neurotechnology. At 8 p.m. we have Metin Akay from University of Houston. And then you can work throughout the whole night if you like. But the next keynote will be on Friday at 11 by Gabriel Pires about his work at Coimbra University in Portugal. And at 1 p.m. Austrian time, we're actually finishing the hackathon. And then the teams should hand over project presentations to me. because we are doing presentations from 2 to 4, so we get 2 hours for all the presentations. The hackathon jury will have a look. Then we get Arno Quipprecht as a keynote speaker, and at 4:30 we are actually doing the ceremony and we are handing over the awards. So here you can see the jury again: Dean Krosienski, Grace, Rigton, Dr. Hirata, Dr. Sacher, Mariam, and also our host in Dubai, which is of course very nice to have all these guys. And if we scroll a little bit further down, then you can already see that we have 4 people registered for the Unicorn Speller Smart Home project. 2 persons are doing the dream painting, 4 persons are doing the Unicorn Sphero, 1 person is registered for the orthosis control. Then we have 3 groups working on FNIRS and the EEG. 3 persons are doing the flight control. 1 person is working on the Unity Rehab. 2 people are registered for the Unity Games project. And we have 2 teams with 5 persons each coming with their own hardware project in. And then we have actually 6 teams working on the stroke rehabilitation data analysis. 2 teams are working on the unresponsive wakefulness data analysis. 1 team working with logged-in patients data. 3 teams with the P300 Speller, and 5 teams with the ECOG data set with the hand poses, and 1 team with the SSVP analysis. You can see that some seats are still empty, where you can still register yourself. And in a few hours, you will receive an invitation to Slack. So we set up a Preneo hackathon account. Every team will be assigned to a certain team. So the teams will have numbers from 1 to 30. Altogether, we have 30 teams registered up to now. And we will just put all your email addresses to a certain team. Then you can contact the other team members to discuss different things. And we have also our experts here. So Johannes Grünwald will help with the data analysis. Christoph Capella will be responsible for data analysis, and Leo Schreiner and Martin Walkshofer will help you with the programming projects. So these are the experts, and if you have questions, you can just click, for example, on Leo Schreiner. Then you can ask him something that you want to know. Or you can communicate just with your own team. So this is called, for example, data analysis, ECOG hand pose. And then you can here find, for example, some publications where the experiment is described. And you find also the MATLAB data. So it's a matrix that you can load into MATLAB, and then you can already do the data analysis. We can also look at the logged in data example. This is again a publication describing the experiment. Then you can see we have data from 2 patients here that you can analyze. For the P300 experiment, we have 5 data sets. For the SSVP, we have the Frontiers publication explaining the experiment and the data. For the stroke analysis, we have some publications here explaining the steps and data from 3 patients before the rehabilitation and afterwards. So you can work on biomarkers, but also on BCI paradigms. This is from coma patients, publication with different data sets. And for the dream painting, for example, you get information, flight control, FNIRS, and so on. And if you want to change the team or the group, then you can post it here. So you can put in your request here that you want to join, for example, the dream painting team, and then we can put you into another team and you will get access to this team. So it's pretty easy to work with Slack, and all the information can just be downloaded from there. Now I'm going back to the Q&A. Nice to see you laughing, of course. We're coming to the end of the summer school. Then we have, you look a bit tired, of course. pleasure. How do we present about our hackathon? So we will use Zoom like during the summer school, and I need afterwards a speaker from every team, and then I can add the speaker into the panel list. I'll show you how this is done. So here in Zoom, I see all participants, and I can add, for example, Daniel to become one of the panelist speakers, and then you can actually give the presentation. So you should actually prepare a PowerPoint presentation. You can also add some videos so that you can give a nice presentation to all the others. Is it possible to watch the lectures without participating in the hackathon? Of course, just log into Zoom and then you can see the lectures like today. Do we get the certificate about the hackathon? Yes, you get the certificate for the hackathon and also one for the summer school. And then, thank you very much for the interesting talk. Daniel, this was for you. Thank you very much. Teams are decided from your side? No. So the most people had wishes in which team they wanted to be, and then we put it together. But you still get the possibility to change from one team to another one. If your friends are maybe located in another team, or if you just want to work on another topic, you can post it here in Slack under the group formation. Where is it? Here, under group forming, you can post your wishes and then we can assign you to somebody else, because you need administrator rights for doing that. Maria, I had registered to the hackathon a while ago. Is it still valid? Of course. So we don't delete people if they're already registered. I haven't received any communication, correct, because the email will go out in about 1 hour, and then you should have the Slack login, and we will show you anyhow tomorrow at 1 how everything is done. So it's pretty simple with Slack and also very efficient. Okay, so seems like all the questions are. Here's one more. Is it advisable to also join the hackathon if you only have basic programming skills? Of course, so we have also artists and non-programmers inside the hackathon, so also neurosurgeons and neurologists and physiotherapists are joining, because it's also very nice and interactive to work together with experts from another field, and this allows you to learn a lot. So you don't need programming skills at all, because during the hackathon, you should also just work out new concepts where brain-computer interfaces can be used. So it's very valuable to have non-programmers inside the teams, of course. Anything else you want to know? Please post it now. I can also check the chat. Victor, I don't have a passport, but I want to join the Brain.io. Can I still participate? What can I do? The passport is only required if you want to borrow hardware. So it's very likely that you don't need a passport at all. If you want to borrow something, an ID card is also good enough. Then we have Deepa. Is there any way I work with you? Just send me an CV. My email is google@g-tec.at. Is it possible to watch the past Zoom lectures? We will put some of the lectures online, but we just need a little bit of time because the videos are so big that it takes really many hours to extract it. Where's the source to learn, please? You will get it on Slack, and then you will see the publications assigned to all the different projects. So we selected the most important publications that you understand, for example, a P300 Speller or SSVP. So if you read this single publication, you will know what you should actually do during the hackathon. What about if we didn't participate? Then you don't get the certificate for the hackathon. And if you watch all the lectures during the summer school, then you get at least a certificate for the summer school. MATLAB is not necessary. You can also use other programming languages. Just the data that we are providing is a MATLAB matrix, but you can of course also export it to other platforms. And for the real-time programming projects, of course, you can work with whatever you want. Okay, let's see the chat, what we have. Is it advisable? I think this was all answered. So thank you very much for today. And here's one. Cecilia, I would like to be part of the Slack Brain.io hackathon group. Can you send me the invitation? Yes, you will get the invitation to Slack if you are registered for the hackathon in about 1 hour. And here you can also already see that there are project numbers. So project number 1 or team number 1 is, for example, Smart Home. Team number 2 is Stream Painting. Team number 3 is Vero, and so on. So you will be assigned to one of these teams, and the numbers will help us to identify in which team you are. Then, I mean, do we need to participate in project to get resources to learn? Yes, you have to sign up for one of the teams to get data sets and publications. Otherwise, we cannot send it to you. So you have to register yourself. Do we need to purchase the g-tec suite? No, you don't have to purchase anything, but you need access to equipment either in our lab or in the Emirates, in one of the labs, or in one of the labs which are participating in the hackathon. If you're working on data analysis, then you can just download the data and you can already go ahead. That's not a question. Hi, Deepa, nice to see you. Why I'm crying? I hope you're crying because you are so happy. Deepa, I'm new to signal processing, so is it possible to work with you? Please send an email to me. I posted in the chat. Somebody likes the key H. So thank you very much for attending today, and I hope to see you tomorrow again. Bye-bye.